For generations, humanity has lived with the belief that our location in the universe was a small planet, orbiting a common type of star inside a galaxy that resembles many others. But recent scientific findings have challenged that long-held assumption. Evidence now suggests that our entire solar system may be positioned inside a very large region of space, with unusually low density, an enormous area spanning hundreds of millions of light-years, where the number of galaxies is lower than average, matter is less concentrated, and large-scale activity appears reduced. How could an entire civilization evolve inside a cosmic void without ever realizing it? And what does it mean for everything we think we know about the universe? Before we embark on this journey, drop it in the comments section where in the world you're watching from and what time it is there now. Echoes from the Big Bang suggest Earth is trapped inside a giant cosmic void, scientists claim. Astronomers claim to have found new evidence supporting a controversial observation that our galaxy is residing in an unusually sparse region in space. This idea has been debated for many years, but new data and new methods of studying deep space are giving researchers more confidence in this strange possibility. The thought of being inside a vast empty region of the universe may feel unusual, but the science behind it continues to grow stronger as more measurements point toward the same direction. The discussion starts with the leftover sound waves and energy waves from the ancient beginning of the universe. These leftovers are often called cosmic microwave background radiation, which is the faint afterglow of the event that took place more than 13 billion years ago. These signals stretch across the entire observable universe. When scientists examine them with advanced telescopes, they do not only look for brightness or temperature, they also study small differences in the signals. These small differences help them understand how matter was spread out shortly after the universe began. When these tiny temperature differences appear in patterns that do not match what theories predict, researchers start asking questions. One of these unexpected patterns suggests that, on a very large scale, our location in the universe might not be as average or typical as once assumed. Many scientists once believed that, wherever you looked in the universe, things should look nearly the same when viewed from far enough away. But some readings show slight differences, and one possible explanation is that the Milky Way galaxy is centered within a region that has less matter than average. A cosmic void is not completely empty. It still contains galaxies, stars, dust and gas, but it contains far fewer than surrounding regions. Think of it simply as an area where matter is spread out thinly across an enormous volume. Instead of countless galaxies packed close together, this region would have large spaces between them. Some voids are so massive that they span hundreds of millions of light-years across. If the Earth and the Milky Way happen to lie near the center of such a void, the effects would show up in how light travels to us from faraway regions. The speed of light is constant, but the brightness and distance of objects can appear different depending on how matter is arranged along the way. In regions with less matter, light passes through more easily. It is less likely to be slowed or distorted. When astronomers observe supernovae, galaxies and other distant objects, they measure the brightness of these objects to understand how fast the universe is expanding. If we live in a low-density region, the appearance of these objects may suggest that the expansion of the universe is happening faster than it actually is. This can create confusion because it mimics effects normally linked to dark energy, which is believed to push space apart. Some scientists have questioned whether the acceleration of the universe's expansion might be partly explained by our location rather than by mysterious energy. That does not mean dark energy does not exist, but it means some observations may be influenced by the shape and structure of the region we're inside. This idea has led to many debates because it challenges some well-established assumptions. For decades, astronomers worked with the belief that Earth does not occupy any special location in the universe, and that any piece of space chosen at random should look statistically similar to any other large piece. The new evidence that is giving strength to the cosmic void idea comes from careful measurements of cosmic microwave background radiation and observations of galaxy clusters. When the afterglow of the early universe passes through large cosmic structures, its temperature and energy change slightly. This effect is called the integrated Sachs-Wolfe effect. If the Milky Way is inside a giant void, this effect should appear in measurable ways, and recent data suggest it does. The strength and direction of these variations match what one would expect if our region contained significantly less matter compared to surrounding space. A giant void around us would have formed naturally if the early distribution of matter in the universe was not perfectly even. Slight differences in density millions of years after the Big Bang could cause some regions to collapse into clusters, and some regions to expand, thinning out matter. Over billions of years, this unevenness becomes more noticeable. Some parts of the universe develop into dense superclusters, filled with tens of thousands of galaxies, while others expand into enormous underdense areas known as voids. These voids are not unusual. What makes this idea surprising is the possibility that we may be positioned quite near the centre of one. Galaxy surveys over the past several decades have created three-dimensional maps of the nearby universe, stretching across hundreds of millions of light-years. These maps show large structures such as the Sloan Great Wall and Laniakea, home to our Milky Way. They also show wide, almost empty areas. Some studies claim that the region around us has fewer galaxies than expected, based on how fast the universe is expanding and how much matter is predicted to exist in this part of space. This mismatch encourages scientists to take the void idea more seriously. Advanced mapping also shows that the number of galaxies in our immediate cosmic neighbourhood is lower than expected by as much as 20% or more. Another clue comes from the behaviour of galaxy clusters, which are the largest gravitationally bound structures in the cosmos. These clusters are expected to be distributed at certain intervals, but some surveys report that clusters near our region are spaced differently than models predict. When clusters appear slightly fewer or slightly farther apart than the mathematical models expect, it signals that space may contain fewer matter-rich regions here than in other directions. This again fits with the idea of being situated in a low-density environment. If the Earth and the Milky Way are inside a giant cosmic void, it might also explain a long-standing puzzle involving measurements of the Hubble constant. The Hubble constant represents the rate at which the universe is expanding. Different methods of measuring it have produced slightly different results. One method involves using supernovae and nearby galaxies. Another involves studying cosmic microwave background radiation. The numbers coming from these two methods have not matched perfectly. Some physicists believe that a cosmic void around us could account for this difference. Light travelling from different regions would be affected differently based on how much matter is present in the space it crosses. The idea is not universally accepted. Many researchers argue that the data can be explained without placing us inside a void. They say that cosmic structures are too large to make such a big difference in global measurements. They also argue that the chances of us being near the centre of a void big enough to influence the expansion measurements are extremely low. But supporters of the void model respond by pointing out that while it may seem unlikely, the universe is full of unusual structural features where large-scale patterns emerge naturally. Telescopes such as the Planck Observatory and the Wilkinson Microwave Anisotropy Probe have provided extremely detailed maps of the cosmic microwave background radiation. These maps show small distortions and slight temperature differences spread across the entire sky. When these small variations are analysed, some alignments and asymmetries appear stronger than expected. One of these is often called the cold spot, a large region of slightly lower temperature. Some scientists think this cold spot may represent the imprint of a massive void located roughly billions of light-years away. Although not all researchers agree on this interpretation, the presence of this cold spot motivates the study of voids even more. If the universe contains voids of various sizes, then it is reasonable to expect that at least one of them could be large enough to influence the measurements astronomers make from Earth. The key question is how large and how empty such a void would need to be. Some models propose that the void would have to be hundreds of millions of light-years wide and have a density reduction of nearly 50% or even more compared to average cosmic density. Observational surveys of galaxies claim that such an underdensity may actually exist, although its exact shape and size remain debated. One of the ways to test the void idea is by studying something called baryon acoustic oscillations. These oscillations are patterns left over from pressure waves in the early universe. They act as a standard ruler that scientists use to measure distances. If the universe has uneven matter distribution, then these oscillations may appear stretched, compressed, or shifted depending on where the void is positioned. Recent studies have begun comparing these oscillations from multiple directions, and subtle inconsistencies suggest that distances may not be uniform everywhere. These small irregularities might be explained by the presence of a massive void influencing the expansion of space in our region. The idea becomes even more fascinating when researchers consider how galaxies move. The motion of galaxies is influenced not only by universal expansion, but also by gravity from surrounding structures. If our region has less mass, galaxies should appear to move outwards slightly faster because there is less gravitational pull holding them back. Some motion patterns observed in galaxy surveys match this prediction. Nearby galaxies show small velocity deviations that appear to align with what would happen if the Milky Way is located in an underdense region. Another line of evidence comes from studying the distribution of hydrogen clouds spread across vast spaces. These neutral hydrogen regions absorb certain wavelengths of light from background objects such as quasars. When astronomers measure how this absorption changes with distance, they gain information about the density of matter across huge stretches. Some of these measurements suggest that the hydrogen density near our region is slightly lower than expected. Although the differences are small, they become meaningful when combined with other clues from galaxy distributions, cosmic background radiation, and cluster counts. Researchers also examine how gravitational lensing behaves in different parts of the sky. Gravitational lensing happens when massive objects bend the path of light. If we lived in an average region with average density, the lensing patterns would match predictions. But some lensing maps show that certain directions contain less matter than the models assume. These directions often align with the region surrounding the Milky Way. Although the differences are small, they add to the overall pattern that supports the void idea. If the Earth and the Milky Way truly lie inside a large cosmic void, it would have interesting consequences for the history of cosmic evolution. Regions with lower density form fewer large galaxies and fewer galaxy clusters. They also produce fewer stars over time because less gas exists to form them. When astronomers compare star formation rates in various regions, they find that the local region of the universe has slightly lower star formation compared to more distant and denser regions. This suggests that the environment around us may naturally be more empty than the cosmic average. Some studies have even proposed that the large-scale structure near our galaxy contains multiple layers of underdense regions that overlap. These layers combine to form what might be interpreted as a giant void with a rough shape, stretching across hundreds of millions of light years in multiple directions. The center of this underdense region appears to be not far from where the Milky Way sits. Although the exact coordinates differ depending on measurement method, the general shape consistently suggests a low-density bubble surrounding us. The measurements of the cosmic microwave background radiation are particularly important because they reflect conditions from more than 13 billion years ago. These signals come from all directions and form a nearly uniform pattern with tiny variations. When these variations show certain alignments, researchers take notice. One alignment, sometimes called the axis of evil, shows that temperature variations appear to line up along a specific direction. Some scientists think these alignments are simply statistical accidents, while others believe they indicate large-scale structures, including voids, influencing the radiation as it travels to us. This giant void idea does not claim that Earth holds a special or privileged place. Instead, it suggests that randomness and natural structure formation could have placed our galaxy inside one of many possible huge voids. With trillions of galaxies across the observable universe, and with a cosmic web of filaments, walls, clusters, and voids stretching across unimaginable distances, it is statistically possible for some galaxies to lie within enormous empty regions. The Milky Way might simply be one of them. As data collection becomes more advanced, astronomers expect to learn more about this possibility. Telescopes capable of scanning billions of galaxies will create more detailed maps of cosmic structure. New instruments measuring cosmic microwave background radiation will produce higher resolution images. More accurate measurements of supernova distances and galaxy motions will help refine the models. Each piece of information contributes to a clearer understanding of whether the Milky Way is truly inside a giant cosmic void, or whether other explanations fit better. What makes this topic especially engaging is how it connects observations across enormous timescales and distances. Leftover signals from the earliest moments of the universe combine with galaxy surveys covering hundreds of millions of light years and supernova measurements stretching across billions of years. Bringing all these pieces together gives scientists a detailed but complex picture of cosmic structure. When all these independent measurements hint toward the same possibility, the idea gains strength, even if it is still debated and far from universally accepted. Some physicists argue that the void idea may help solve multiple cosmic puzzles at once. Besides addressing the Hubble constant tension, It might provide new explanations for unusual temperature asymmetries in the cosmic microwave background radiation. It might also help explain why some galaxy clusters appear to be moving in a strange bulk flow, as if being pulled by a large unseen structure. It might also help explain why some galaxy clusters appear to be moving in a strange bulk flow, as if being pulled by a large unseen structure. If the void is asymmetric or connected to other larger underdense regions, it could influence galaxy motions on scales of hundreds of millions of light years. The search for answers continues as scientists examine more fine details within the cosmic microwave background radiation. Researchers measure not only temperature differences but also polarization patterns. Polarization reveals how the light waves were pushed or pulled by matter in their path. Some polarization patterns appear slightly off from theoretical predictions, suggesting uneven distribution of matter. These small irregularities add subtle support to the idea that our region may not have the same density as the average universe. Studies of quasars, some of the brightest objects in the universe, offer another set of clues. These distant objects shine with such intensity that they can be used as background lights to probe the material between galaxies. When quasar light travels through space, it passes through gas, dust, and other structures. By analysing how this light is absorbed or shifted, astronomers create detailed maps of cosmic matter across distant scales. Some quasar observations show less absorption in directions near our local region, suggesting less material overall. This pattern fits with the characteristics of a void. Another interesting factor is the temperature of galaxy clusters. Clusters containing more matter often appear hotter because gases trapped in these structures are compressed and heated by gravitational forces. When researchers measure the temperature of clusters in different directions, slight variations appear. Some clusters in our local region seem slightly cooler than clusters in denser regions. While this difference is small, it supports the idea that our region contains fewer massive structures. Even the motion of our own galaxy is sometimes considered when studying the void hypothesis. The Milky Way is moving at high speed relative to the cosmic microwave background radiation. This motion is partly due to gravitational attraction from dense regions, and partly due to the expansion of the universe. Some physicists have proposed that if our galaxy lies within a large void, this position could partly explain the speed and direction of our motion. Although this idea is still speculative, it remains part of the broader discussion. As research continues, more tools and methods develop. Computer simulations play an important role in testing how voids affect cosmic measurements. These simulations recreate the early universe, allow matter to evolve over billions of years, and compare results to real observations. Some simulations produce regions similar to the supposed void around the Milky Way, suggesting that such structures can form naturally without breaking any major cosmic rules. These simulated voids help researchers understand how light would travel through such regions, how galaxies would form in them, and how supernova brightness would appear from inside them. One of the most compelling ideas is that a large cosmic void might slightly exaggerate the brightness distances astronomers measure from Type Ia supernovae. These supernovae are reliable distance markers because their brightness is predictable. But if the surrounding space has less matter, the light from these supernovae may appear slightly brighter than expected. This could trick astronomers into thinking that the universe is expanding faster than it actually is. Supporters of the void hypothesis say this may account for part of the acceleration normally attributed to dark energy. Some researchers combine multiple lines of evidence by looking at galaxy counts, supernova brightness, cosmic microwave background radiation, baryon acoustic oscillations, and gravitational lensing all at once. When they overlay these datasets, certain patterns become clearer. One pattern repeatedly found is that large sections of the sky near our region contain fewer galaxies and weaker lensing signals. These features match the predictions of an underdense environment. The idea also gains interest because it might reshape how scientists understand cosmic acceleration. Instead of assuming dark energy behaves in a certain way, some physicists consider that the uneven distribution of matter across giant cosmic scales might play a larger role in shaping expansion rates than previously thought. If this is true, then the cosmic void surrounding the Milky Way is not just a curiosity but a key factor in how we interpret the universe's behavior. As the field develops, astronomers pay close attention to statistical significance. A claim about a cosmic void must be supported by strong numbers. Over the years, as more galaxy surveys and cosmic microwave background observations become available, the statistical support for a local underdensity has slowly increased. While not yet confirmed beyond all doubt, the evidence continues building in a way that encourages further investigation. The possibility of living inside a giant cosmic void adds a fascinating layer to our understanding of the universe. It shows that the cosmos is not perfectly smooth or uniform. Instead, it contains enormous structures created by tiny differences in the early distribution of matter. Whether or not the Milky Way truly lies within one of these massive underdense regions is still under study, but the growing body of data shows that this possibility cannot be dismissed. Observations across many wavelengths, from radio to optical to microwave, show patterns that fit naturally with the void scenario, creating an ongoing and active area of research in modern cosmology. The KBC void, which some scientists also call the local hole, is known today as one of the most immense and surprisingly empty regions ever identified in our cosmic neighbourhood. It carries the initials of 3 astronomers, Ryan Keenan, Amy Barger, and Lennox Cowie, who studied this mysterious region in the year 2013. Their work drew attention to something unusual that seemed to stretch across an extraordinarily large part of the universe. Before their research, many scientists suspected that space contained large empty regions known as voids, but the size and location of this one made it especially interesting. Ever since then, countless studies, papers, and discussions have tried to understand what this gigantic low-density area means for the way the universe behaves and how its expansion is measured. The region is described as an underdensity, which means it contains much less matter than average when compared to the rest of the observable universe. Even though outer space is already very empty compared to anything we experience on Earth, voids take this emptiness to another level. Yet even with all this emptiness, the KBC void is still not completely hollow. It contains galaxies, stars, cosmic gases, dark matter, and many important structures. What makes it special is that it contains far fewer galaxies and less mass than would normally be expected in a region of the same size. According to the researchers who studied it, this underdense area appears to be roughly spherical in shape, with an astonishing diameter of around 2 billion light-years, which is equal to roughly 600 megaparsecs. To imagine such a size, one would have to think about a region so enormous that light, which travels faster than anything in the universe, would still require around 2 billion years to cross from one side to the other. Inside this enormous region sits the Milky Way galaxy, which is the home of our solar system, our sun, and countless stars. The local group, the cluster of galaxies that includes the Milky Way, Andromeda, and dozens of smaller galaxies, is also inside this giant low-density bubble. Even more surprising is that a significant portion of the larger Laniakea supercluster lies within the boundaries of this vast underdense region. The Laniakea supercluster itself extends across many hundreds of millions of light-years and contains hundreds of thousands of galaxies spread across a mind-stretching volume of space. Yet even with all of this inside it, the KBC void is still considered empty compared to the surrounding universe. The position of our galaxy inside this cosmic bubble is also interesting. The Milky Way is located only a few hundred million light-years from the center of the void, meaning we're not near the edge but somewhere close to the middle of this unusually empty space. This fact has fascinated researchers because being located near the center of such a large underdensity could influence the way we measure the universe around us. If the space around us has less matter, then it expands differently than expected, and this can affect the measurements scientists make when they try to determine how fast the universe is stretching outward. The question of how the KBC void fits into the standard cosmological model remains one of the biggest debates among scientists. The most widely accepted model of the universe is called the Lambda Cold Dark Matter Model, or LCDM for short. This model includes the idea of dark energy, which is symbolized by the Greek letter lambda, and cold dark matter, which refers to a form of matter that does not interact with light, but has mass and helps shape the universe on large scales. According to LCDM, the universe contains both dense regions like galaxy clusters and underdense regions like voids. However, the size of the KBC void seems unusually large, far bigger than what some researchers believe should exist if the LCDM model is correct. For example, one group led by Hasselbauer and others has argued that a void as enormous as the KBC void does not fit within the limits of the LCDM model. They claim that according to computer simulations and theoretical predictions, regions this empty and this large should be extremely rare if not nearly impossible. Their argument has added fuel to the idea that something unusual is happening in our cosmic neighbourhood, something that may require a new understanding of how the universe works. However, other researchers disagree with this conclusion. A separate team led by Salane and colleagues has argued that the existence of supervoids, including one as large as the KBC void, can still be consistent with the LCDM model. They believe that even though voids of this size are rare, they are not impossible. According to their analysis, supervoids such as the KBC void can form naturally in a universe that follows the rules of LCDM, and seeing one near us does not necessarily mean the model is incorrect. The debate continues partly because measurements of the large-scale structure of the universe are extremely complex. The universe contains billions of galaxies arranged in a vast cosmic web of filaments, clusters, and voids. Trying to determine exactly how dense or underdense a region truly is can be challenging, especially given the limits of what we can observe directly. Even small differences in the way the data is interpreted can lead to large disagreements about whether a structure like the KBC void is unusual or expected. One of the most important reasons scientists care about the KBC void is because of its potential impact on the measurement of the Hubble constant. The Hubble constant is a number that tells us how fast the universe is expanding. It is calculated by measuring how quickly galaxies move away from us depending on their distance. But in recent years, different methods of measuring the Hubble constant have given different results, and this disagreement has become known as the Hubble tension. Measurements that use galactic supernovae and Cepheid variable stars tend to give a Hubble constant in the range of 72 to 75 km per second per megaparsec. On the other hand, measurements that come from observing the cosmic microwave background, the faint leftover radiation from the Big Bang, and baryon acoustic oscillation data tend to give a lower number, usually around 67 to 68 km per second per megaparsec. This difference is significant because it suggests that the universe might be expanding at different speeds depending on how it is measured, or that our understanding of cosmology may be incomplete. This is where the KBC void becomes important. Galaxies that are inside a large void experience gravitational forces from the massive regions outside the void. These forces can pull galaxies outward toward the denser areas of the universe. This outward motion can make the local region appear to be expanding faster than it actually is. In other words, if our galaxy is located inside a large underdense region, then our local measurements of the Hubble constant might naturally come out higher than the true global value. Some researchers have proposed that the KBC void could be the explanation for the Hubble tension. If we are living inside a giant underdensity, then the expansion rate we observe in our local region could be affected by the gravitational pull of the surrounding denser regions. This would make it look like the universe is expanding faster here than it is elsewhere. Several studies have suggested that considering the KBC void could help bring the two different measurement methods into agreement, reducing or even removing the Hubble tension. Even more intriguing is that data from baryon acoustic oscillations presented at the National Astronomy Meeting in the year 2025 showed that a void model is around 100 million times more likely than a model that assumes no void at all while still trying to match the Planck cosmology measurements. This result strongly suggests that including a large underdensity like the KBC void in cosmological models could lead to better alignment with actual observations. Such a huge difference in likelihood has encouraged more researchers to take the void explanation seriously. However, not all scientists agree. Other studies have examined large-scale galaxy surveys and found no convincing evidence of a void as large or as empty as the KBC void appears to be. These studies argue that observations extending beyond the claimed radius of the KBC void do not show the expected signs of such a massive underdensity. According to these researchers, the universe around us does not seem to behave as if we are inside a giant void. Instead, they believe the distribution of galaxies and dark matter is more uniform than the void model would suggest. But even these counter-arguments have problems. Important issues were identified in their analysis, suggesting that their conclusions may not be as reliable as initially thought. In fact, later work pointed out that the methods used to measure the density of galaxies beyond the void may not have been accurate enough to rule out the existence of such a large underdensity. These shortcomings reopen the possibility that the KBC void might indeed be real, and that it could have significant effects on cosmological measurements. Another fascinating twist to the story came from studies involving MOND, which stands for Modified Newtonian Dynamics. MOND is an alternative theory to standard gravity, proposing that at very low accelerations, such as those experienced in the outskirts of galaxies or in large cosmic structures, gravity behaves differently from what general relativity predicts. While MOND is not widely accepted as a replacement for general relativity, it has been surprisingly successful in explaining certain galactic rotation curves without requiring dark matter. Researchers who applied MOND to the KBC void proposed that the outflow of matter from the void could help explain the Hubble tension more effectively than classical models. They suggested that the large underdensity combined with MOND gravity could generate a velocity field that matches what we observe in the local universe. This means that instead of needing to revise the standard cosmological model completely, one could combine MOND with the existence of the KBC void to explain several puzzling observations at once. Later studies found something even more remarkable. The outflow model successfully predicted the bulk flow curve, which is an important measure of how matter moves on large scales in the local universe. The bulk flow refers to the average motion of galaxies within a huge region of space, often hundreds of millions of light years across. Accurately predicting this curve is extremely difficult, yet the void-based MOND model appeared to match the observations very well. This gave additional support to the idea that the KBC void might be responsible for many strange features in the expansion of the universe around us. The seriousness of this discovery lies in the fact that the bulk flow is not just a small detail, but a major cosmological measurement. If the void model can correctly describe how galaxies move relative to each other over vast distances, then it may offer a deeper understanding of how our local universe is shaped and how gravity works in low-density regions. Such results also raise new questions about whether the standard model of cosmology might need adjustments, or whether alternative theories like ChemWand should be considered more carefully. The existence of such a huge void has larger implications for the way galaxies form and evolve. In an underdense region, there are fewer interactions between galaxies. This means fewer collisions, fewer mergers, and fewer gravitational encounters that can trigger star formation or shape galactic structures. Over billions of years, galaxies inside a void can develop differently from those in more crowded regions. Some studies suggest that galaxies living inside voids tend to be smaller, less massive, and less active in forming new stars. Others propose that the environment could encourage more isolated and unusual galaxy types, giving rise to strange structures that are rare elsewhere. If the KBC void is as large as estimated, then it means our galaxy has been living in a quieter, less crowded part of the universe for billions of years. This peaceful environment could have influenced the Milky Way's history, its shape, and even the development of its spiral arms. Some researchers argue that the relative calm of this region may have indirectly played a role in the stability of our solar system over immense time spans. While this idea remains speculative, it contributes to the growing interest in how large-scale cosmic geography affects the evolution of galaxies and the potential for life. Another intriguing aspect of the KBC void is how it connects to the overall structure of the cosmic web. The universe is not evenly filled with matter. Instead, it resembles an enormous network of filaments, clusters, and empty spaces. In some ways, the cosmic web behaves similarly to a sponge, with dense regions connected by thin bridges and huge hollow pockets in between. The KBC void, if confirmed, would be one of the largest of these pockets known near our galaxy. Large voids like this also affect how light travels across space. As light passes through regions with different densities, its path and speed can be influenced by gravitational fields. This means that light coming from distant galaxies may be slightly distorted or stretched when it reaches us. If scientists do not properly account for the presence of such a large void, they may misinterpret these distortions as signs of a different expansion rate or other cosmological effects. This adds even more pressure to determine whether the KBC void truly exists and how empty it really is. Understanding the KBC void also helps astronomers refine tools like redshift measurements. Redshift is used to determine how fast galaxies are moving away due to the expansion of the universe. But if the region between us and those galaxies is underdense, then redshift might behave differently. This is because galaxies in or near a void can be influenced by gravitational acceleration from surrounding denser regions, altering the velocities we observe. As a result, any slight error in estimating the density of the region could lead to large discrepancies in cosmological measurements. The continuing debate has led researchers to collect more data using both ground-based telescopes and space observatories. New sky surveys continue mapping galaxy distributions with better precision. Each new set of observations helps refine the models, correct earlier assumptions, and fill in missing details. As more galaxies are catalogued and more precise measurements are made, the picture of the KBC void may eventually become clearer. One promising approach involves using infrared telescopes to peer deeper into dusty or faint regions where optical telescopes struggle. Infrared light can reveal galaxies that would otherwise be invisible, reducing the risk of underestimating how many galaxies exist within a given region. Some early results from infrared surveys have suggested that the local universe may indeed contain fewer galaxies than expected, which supports the idea of an underdensity. Other surveys, however, show a more uniform distribution, keeping the debate alive. More advanced observations will also come from gravitational wave detectors. When massive objects like black holes or neutron stars collide, they emit ripples through space-time. These waves can provide new clues about the distribution of matter in the universe. If the KBC void is real, it might influence the timing and strength of gravitational waves that pass through it. Comparing the behavior of these waves in different directions might reveal subtle differences in the density of space around us. Another important factor to consider is the distribution of dark matter within the void. Dark matter does not emit or reflect light, so it cannot be seen directly. Scientists detect it by studying its gravitational influence on visible matter. If the KBC void is truly underdense, then the amount of dark matter inside it should be significantly lower than average. Studies using gravitational lensing, where light from distant galaxies is bent by gravity, can help measure how much dark matter is present. Current gravitational lensing observations show hints of an underdensity, but the data is still not conclusive. Cosmologists are also exploring how the temperature of the cosmic microwave background might be affected by a large void. Light from the cosmic microwave background travels across the entire universe before reaching Earth. If it passes through a massive underdensity like the KBC void, it can experience a slight energy change due to a phenomenon known as the integrated Sachs-Wolf effect. Detecting this effect would provide additional evidence for the void, but measurements so far are noisy and require more precise analysis. The role of cosmic neutrinos is another area of interest. Neutrinos are extremely light particles that travel through space almost without interacting with anything. Their distribution and speed can give clues about the density of matter in different regions of the universe. Because neutrinos respond very weakly to gravitational effects, they can pass through voids almost unaffected. Studying the behavior of neutrinos coming from different directions may reveal differences caused by the presence of the KBC void. The existence of a region billions of light-years across with significantly less matter than average forces scientists to rethink assumptions about randomness in cosmic structure formation. While voids of various sizes are known, a void of this magnitude in such a local position is something extraordinary. Some cosmologists argue that it may require new physics, while others insist that it fits naturally within existing theories. This ongoing debate fuels more studies, more observations, and more attempts to reconcile theory with the data we collect from the universe around us. The giant void is one of the most astonishing regions ever found in the entire universe because of how unusually empty it is. It sits in a part of the sky marked by the constellation known as Canes Venatici, a constellation whose name means the hunting dogs. In this region, the number of galaxies is far lower than what astronomers normally expect to see when they look deep into space. Instead of the usual bright clusters and long cosmic structures that fill most parts of the universe, this area stretches across an unbelievable amount of space and contains far fewer galaxies than average, making it stand out as a place of extraordinary emptiness. The giant void is considered the second largest confirmed cosmic void ever discovered. The scale of this emptiness is almost impossible to grasp using everyday ideas because the numbers involved are far beyond human experience. It spans an estimated diameter of between 300 and 400 megaparsecs, which translates to roughly 1 billion to 1.3 billion light-years across. Light itself, the fastest thing known to exist, would need more than 1 billion years to travel from one side of this void to the other, and that alone gives a sense of the unimaginable size of this structure. In comparison, our own Milky Way galaxy is around 100,000 light-years wide, meaning the giant void is about 10,000 times wider than our galaxy. Even if someone could travel at the speed of light, they would still spend a time longer than all of human history traveling across it. The center of the giant void lies around 460 megaparsecs away from Earth, or about 1.5 billion light-years. When astronomers say that the void is at a redshift of 0.116, they are describing how much the light coming from that region has been stretched due to the expansion of the universe. This stretching of light, known as redshift, helps astronomers calculate how far away cosmic objects are. In this case, that redshift value perfectly matches the enormous distance of around 1.5 billion light-years. This gigantic empty region was discovered in the year 1988 by astronomers studying the distribution of galaxies in the sky. At the time of its discovery, it was recognized as the largest void in the northern galactic hemisphere, meaning the half of the sky lying above the plane of our Milky Way galaxy. The detection of such a huge emptiness shocked many researchers, as cosmic voids were still poorly understood at that time. Although astronomers had found other voids earlier, none were expected to reach this unbelievable size. As studies continued, the giant void was confirmed to be possibly the second largest void ever recorded in the entire observable universe. Many people often hear about another well-known cosmic void, the hypothesized Eridanus supervoid, which has been suggested as the reason behind a strange cold region seen in the cosmic microwave background, the faint radiation left over from the birth of the universe. The Eridanus supervoid is often linked to the so-called WMAP cold spot, a region of the sky that appears cooler than its surroundings when measured by the Wilkinson microwave anisotropy probe. Even though this hypothetical supervoid has gained attention because of its connection to that cosmic cold spot, it is still smaller compared to the giant void. In fact, the giant void dwarfs the Eridanus supervoid in size, stretching across a larger and more impressive region of space. However, unlike the Eridanus supervoid, the giant void does not seem to be connected to any major cooling or unusual temperature variation in the cosmic microwave background. This means that even though it is huge, its presence does not leave a strong imprint on the ancient radiation left over from the early universe. Inside this immense expanse of space, which is mostly empty, astronomers have found around 17 galaxy clusters. These clusters are grouped in a roughly spherical region that is around 50 megaparsecs wide. The fact that only 17 clusters appear within such an enormous volume shows how sparse the matter is inside this void. Normally, in denser parts of the universe, galaxy clusters gather together under their mutual gravitational pull, forming large structures. But in this void, the clusters appear unusually isolated, drifting within a sea of emptiness with very little influence from one another. When scientists studied how these clusters move, they found something surprising. The clusters show almost no interaction with each other at all. Their gravitational effects on one another are so weak that they behave as if they are floating alone. In most parts of the universe, galaxy clusters tug on each other through gravity, drifting together over long timescales, merging, or forming larger structures. But inside the giant void, the clusters are too far apart and too few in number for this to happen. The density of matter inside the void is extremely low, weakening gravity's ability to connect these clusters. As a result, each cluster drifts through its lonely patch of space almost unaffected by the others. The location of the giant void in the sky is also interesting for another reason. It lies close to another famous cosmic void known as the Boötes void. The Boötes void is one of the first enormous voids ever discovered, and is sometimes called the Great Nothing due to its enormous emptiness. Even though the Boötes void is also incredibly large, the giant void surpasses it in scale. The closeness of these two massive voids in the same general region of the sky raised many questions for astronomers trying to understand how such enormous empty areas formed. It suggested that this part of the universe experienced unique conditions during its early development, which might have prevented large numbers of galaxies from forming. Between the years 2004 and 2006, cosmologist and theoretical physicist Laura Mersini-Houghton proposed a fascinating idea that connected the giant void with something even more mysterious: the multiverse. The multiverse is a concept suggesting that our universe might not be the only universe that exists. Instead, there could be many universes, each with its own physical laws, properties, and cosmic structures. According to her theory, our universe might have originated from a much larger multiverse, and the unusual features we see today, including huge cosmic voids, might be evidence of interactions between our universe and other universes beyond our cosmic horizon. Laura Massini-Houghton suggested that early in the history of the universe, before galaxies and stars formed, our universe might have been influenced by neighbouring universes. These interactions could have created patterns or irregularities in the cosmic landscape. In her series of research papers, she made several predictions that could be tested using astronomical observations. One of those predictions was that enormous voids should exist in certain parts of the sky because the early interactions between universes could have left behind large imprints in the form of regions where matter was unusually scarce. When the giant void was later studied and confirmed to be one of these enormous empty regions, her theory gained additional interest because it seemed to match her predictions. Her work suggested that the presence of the giant void might not just be a random event that happened due to normal cosmic evolution. Instead, it might be a sign of something deeper that happened in the earliest moments of existence. The possibility that such a large void could be linked to events that occurred before the formation of galaxies, or even before the universe fully emerged from its earlier stages, captured the curiosity of scientists. Although the idea of the multiverse remains controversial and hard to prove, the existence of a void as large as the giant void encourages researchers to explore whether these giant structures could indeed be leftovers from interactions with regions beyond our universe. As astronomers studied the giant void more deeply, they found that the emptiness inside it seemed too extreme to be explained by ordinary cosmic evolution alone. In the standard model of cosmology, matter spreads out unevenly at first because of tiny fluctuations that occurred shortly after the Big Bang. Over billions of years, these small differences cause matter to clump together in some places and thin out in others. Galaxies, stars, and clusters form where matter is dense, while voids appear where matter is sparse. But the giant void appears to be so enormous and so underdense that scientists wondered whether something else contributed to its formation. Structures of this size are rare, and their existence encourages questions about whether unknown processes shaped the universe during its earliest moments. When astronomers map the universe, they often describe it as looking like a vast cosmic web. The web contains long filaments of galaxies, massive clusters, superclusters, and huge empty bubbles. The giant void stands out as one of the largest bubbles of emptiness known. The presence of 17 small clusters inside the void shows that it is not completely empty, but even with those clusters, the void remains one of the most extreme examples of cosmic underdensity. The clusters appear like tiny islands floating in a vast ocean of nearly empty space, surrounded by distances so large that galaxy interactions become nearly impossible. The giant void also helps astronomers understand how gravity shapes the universe. In regions of high density such as galaxy clusters, gravity works strongly, pulling objects together over time. But in a void, gravity is too weak to draw material inward. Instead, the expansion of the universe pulls galaxies away from each other faster than gravity can pull them together. This means that voids tend to expand faster than other regions of the universe, making them grow larger over time. The giant void, with its enormous size, shows how powerful this expansion can be when matter is spread too thinly for gravity to overcome it. Another important aspect of the giant void is its relationship to dark energy, the mysterious force driving the accelerated expansion of the universe. Some researchers believe that studying extremely large voids like the giant void can help reveal whether dark energy behaves the same everywhere, or if it varies across different parts of the universe. If the behavior of galaxies and clusters inside voids differs from predictions, it might provide clues about the nature of dark energy. Since the giant void is one of the largest laboratory zones for studying this effect, it draws interest from cosmologists trying to solve one of the greatest mysteries in modern science. When Laura Massini-Houghton put forward her predictions about the multiverse and the existence of giant voids, she suggested that these voids might be areas where the influence of other universes reduced the amount of matter available in our own universe. According to her theory, the boundary between universes might have affected the density of matter in certain places, leaving behind imprints that we can observe billions of years later. This theory helped shift the conversation about voids from simply considering them random occurrences to viewing them as possible indicators of a much larger cosmic picture. As the years passed and astronomers gathered more data, the giant void continued to stand out as one of the most puzzling and significant structures ever found. Its size, its emptiness, the lonely clusters drifting inside it, its closeness to another major void, and its potential connection to early cosmic events make it one of the most fascinating subjects in modern astrophysics. Every detail about the giant void invites deeper study, from the way galaxies inside it move to the way it fits into the vast cosmic web. The 17 clusters inside the void provide a rare opportunity to study how galaxies behave when they are isolated. Normally, galaxies inside clusters move under the combined gravitational pull of thousands of neighbours. But inside the giant void, these clusters move as if they are almost alone. Their motions are slower, less chaotic, and show patterns that tell astronomers how gravity behaves in regions of extremely low density. This can help researchers test theories about dark matter, galaxy evolution, and the long-term future of the universe. Because the giant void lies so far away, around 1.5 billion light-years, astronomers see it as it was 1.5 billion years in the past. When someone looks at the sky, they are not seeing the universe as it exists today, but as it existed when the light from those distant regions began its journey toward Earth. So the clusters inside the giant void appear the way they were long before complex life evolved on Earth. Astronomers must infer what the void looks like today using models that show how voids grow over cosmic time. Most likely, the void has expanded even more since the light we observe left its edges, meaning the giant void could be even larger now than current measurements suggest. Even though voids may seem like empty, featureless parts of space, they are actually essential to understanding how the universe works. They help balance the cosmic web by providing vast regions where expansion dominates over gravity. Without voids, the distribution of galaxies would look very different, and the universe would not have the same web-like structure seen today. The giant void represents an extreme example of this balance, pushing the limits of how large voids can grow within the known laws of physics. The discovery of such a gigantic empty region in the late 1980s changed how scientists mapped the universe. At that time, large surveys of galaxies were just beginning. As astronomers charted the positions of galaxies across the sky, they created the first three-dimensional maps of the universe. These maps revealed the cosmic web, the interconnected pattern of filaments, clusters, and voids. The giant void stood out in those maps as a huge gap, a dark region where very few galaxies appeared. This discovery showed that the universe was far more complex and more structured than earlier theories had predicted. When researchers later compared the giant void to other known voids, including the Boötes void, they realized that the size of the giant void pushed the boundaries of what standard models of cosmic evolution could easily explain. This led to many discussions about whether rare early fluctuations in the density of matter could have produced such an enormous void. Some simulations showed that while it is extremely unlikely, it is still possible for such a large void to form naturally. Other simulations suggested that the probability is so low that other explanations, including exotic physics, might be needed. The area surrounding the giant void also became a focus of study. The fact that the void is located near the Boötes void hints that this region of the universe may contain an unusually large concentration of underdense areas. This raised questions about whether several voids may have merged over billions of years to form one supervoid, or whether the early universe produced larger than usual gaps in certain directions. The idea that cosmic voids might merge like expanding bubbles is supported by some theoretical models, which show that when voids expand, their edges can eventually touch and merge, creating even larger empty regions. Observations of the 17 clusters inside the void revealed more interesting details. The clusters are not evenly spread out but are concentrated in the central spherical region. This suggests that even in a giant void, some places still had enough matter to form galaxy clusters, while the surrounding regions had far too little. The clusters appear like the last survivors of a once richer region of space that became stretched out and thinned over cosmic time. The motion of these clusters also tells astronomers how the void is expanding. Since gravity is weak inside a void, clusters drift outward as space expands. Measurements show that the clusters inside the giant void move differently from galaxies in denser regions. Their isolated behavior provides a unique way to test theories about cosmic expansion and dark energy. The lack of strong gravitational interactions among the clusters also hints at how little dark matter exists inside the void. Dark matter plays a major role in shaping the universe because it provides the hidden mass that creates most of the gravity in cosmic structures. In dense regions, dark matter pulls galaxies together. But in a void, both ordinary matter and dark matter are scarce. The 17 clusters inside the giant void likely contain most of the dark matter in that region. but even that amount is too little to draw them close enough to form larger structures. The giant void also challenges scientists to think about the early conditions of the universe. If the universe began with small variations in density, how did one region become so extremely underdense? Did rare fluctuations in the early universe grow into giant voids like this one? Or did interactions with something outside our universe influence the distribution of matter? These questions continue to inspire new research, new simulations, and new theories. The idea that our universe might have been shaped by interactions with other universes is one of the boldest theories connected to the giant void. In Laura Massini-Houghton's view, a void of this size could be a leftover signature of such an interaction. If another universe once lay close to ours in the early moments after the Big Bang, the boundary between them could have affected how matter settled. Regions closer to the boundary might have experienced forces that pushed matter away, creating unusually large voids. In her research papers published from 2004 to 2006, she described how such voids could appear in specific locations and predicted that observations of the sky would eventually reveal them. The Buta's Void, often called the Great Nothing, stands as one of the most unusual and puzzling regions ever identified in the observable universe. It is a roughly round area sitting near the direction of the constellation known as Boötes, a constellation that has been recognized for many centuries. Yet just beyond that familiar pattern of stars lies something incredibly strange, something so empty and so vast that it challenges the human sense of scale. While most regions of the universe, even the darker and quieter ones, contain a sprinkling of galaxies scattered across space, this particular region contains only about 60 galaxies. When astronomers calculated how many galaxies should exist within a space this large, they arrived at a number closer to about 2,000. That means the Buta's Void holds only a tiny fraction of what is expected, making it shockingly underpopulated, one of the largest known empty spaces ever discovered, and a place often called a supervoid because of its extraordinary size and extreme scarcity of matter. The Buta's Void stretches outward with a radius of about 62 megaparsecs, which is equal to nearly 330 million light-years. A single light-year is already an enormous distance, the span that light travels in 1 year at a speed of nearly 300,000 kilometers per second. When one thinks about millions of light-years, or even hundreds of millions, the mind begins to strain as it tries to grasp distances that lie far beyond anything the human body or the human imagination naturally experiences. Yet this void reaches across hundreds of millions of these units, making it one of the largest gaps or hollows ever found within the structure of the universe. Even the word void does not fully communicate the scale. It is not simply an empty room or a cavity carved into some large object, nor is it similar to the empty space found between planets or stars. Instead, it is a titanic cosmic-sized gulf in which galaxies themselves, those massive systems made of stars, dust, gas, and dark matter, are unusually rare. The discovery of this vast and lonely region occurred in the early 1980s. In the year 1981, astronomer Robert Kirshner and his colleagues were conducting a major study of galactic redshift. Redshift refers to the way light stretches as galaxies move away from us due to the expansion of the universe. By carefully measuring these shifts, astronomers can figure out how fast galaxies are receding, how far away they are, and how they are arranged across the sky. Kirshner's survey was not just a routine mapping task. It was a sweeping exploration designed to uncover large-scale patterns in how galaxies cluster, disperse, and form long chains or walls. During this survey, the team came across something they did not expect. In one part of the sky, their observation showed a gigantic gap, a region with very few points of light registering as distant galaxies. This was not a small irregular patch, or a minor deviation from expected cosmic density. It was a profound absence, a void of such immense scale that it was immediately recognized as something unusual. Kirshner's team soon realized that they had stumbled onto one of the largest known voids in the visible universe, something so oversized and so empty that it stood apart from the usual cosmic patterns seen elsewhere. The central point of the Buta's Void lies roughly 700 million light-years away from Earth. When astronomers describe such a distance, they are referring to the time it takes for light to reach us. In other words, the light we now detect from galaxies near the center of the void left those galaxies about 700 million years ago, long before humans existed and even before many ancient species that once lived on our planet had emerged. The coordinates of the void's centre fall at a right ascension of 14 hours and 50 minutes and a declination of 46 degrees, placing it in a specific mapped position on the celestial sphere used by astronomers to pinpoint locations in the sky. These coordinates help scientists know exactly where to observe when sending powerful telescopes to study the Great Nothing. Scientists studying the Bhuta's void were initially struck by its enormous radius, its striking lack of galaxies, and its smooth, rounded shape. These features raised questions. Was this gap the result of something unusual in the early universe? Did some event or force clear out the matter that would normally have gathered to form galaxies? Was this empty region a sign that something about our understanding of cosmic evolution needed to be improved? As research continued, astronomers began to find answers that fit within the broader, widely supported model of how the universe forms and changes over billions of years. This model is known as the lambda-cold dark matter model, often shortened to LCDM. It is the most successful and widely accepted explanation for how cosmic structures, from tiny clumps of matter to enormous galaxy superclusters, arise through the interactions of normal matter, dark matter, and the repulsive push of dark energy represented by the lambda term. The presence of the Bhuta's void does not contradict this model. In fact, it appears to fit surprisingly well within the LCDM explanation of how matter clumps in some regions, while leaving other regions wide open and mostly empty. The universe is not evenly filled. Instead, it resembles a kind of three-dimensional network. Across this network, galaxies gather along filaments or sheets, thin, long structures that stretch across enormous distances. Between these filaments and sheets lie large, bubble-like spaces containing far less matter. These are voids. Some are small, some medium, and a few, like the Bhuta's void, are enormous. One hypothesis developed to explain how the Bhuta's void became so unusually large is the idea that multiple smaller voids gradually merged over a long period of cosmic history. In the early universe, the matter was not perfectly smooth. Some areas held slightly more mass, others slightly less. Gravity slowly pulled higher density areas together into galaxies and clusters, while lower density areas expanded into emptier regions over time as surrounding matter was pulled out toward denser zones. If several low-density areas sat near one another, they could gradually merge, forming a much larger void. The Bhuta's void may have formed in exactly this way, combining several earlier hollows into one supervoid. This process may have taken hundreds of millions or even billions of years. This merging theory also helps explain why the Bhuta's void is not entirely empty. Even though it contains only about 60 galaxies instead of the expected 2,000, those few galaxies are arranged in a noticeable pattern. They sit along what appears to be a roughly cylindrical shape running through the centre of the void, almost like a thin thread stretching across the hollow. This thin distribution of galaxies is thought to be the remnant of the earlier boundaries between smaller voids that eventually joined together. In the zones where those boundaries once existed, a small amount of matter likely accumulated more than in the central areas of the void. As time passed, these slightly denser strands of matter formed small groups of galaxies, creating the faint pattern astronomers observe today. The galaxies inside the Bhuta's void are themselves fascinating because they exist in such a lonely environment. While galaxies within densely populated regions interact frequently, sometimes colliding, merging, or passing close enough to influence each other with gravity, the galaxies in this supervoid are far more isolated. Their development may have been slower, quieter, and shaped by fewer interactions. Studying them offers valuable insight into how galaxies behave when they grow with minimal interference from their cosmic neighbours. The few galaxies within the void may also show different shapes, structures, and rates of star formation compared to galaxies surrounded by many others. When astronomers first discovered this mega-empty region, its sheer size inspired many discussions and even some imaginative speculation. The idea of a supervoid stretching hundreds of millions of light-years fuels questions about how matter is arranged across cosmic distances. Some early observers even wondered whether the Bhuta's void might hint at some unusual process in the early universe, such as the influence of exotic forms of matter or energy. However, research continued with improved telescopes, better modelling techniques, and more extensive surveys. Each new study strengthened the view that very large voids can form naturally within the LCDM framework. Simulations of the early universe have shown that when matter begins with small irregularities and is left to evolve under the influence of gravity and dark energy, large voids like the Bhuta's void can indeed appear over the course of billions of years. Despite this scientific reassurance, the Bhuta's void continues to fascinate both astronomers and the public. Its vastness is difficult to fully grasp. If the Milky Way galaxy were placed near the centre of this enormous cosmic hollow, it would be surrounded by emptiness stretching out for hundreds of millions of light-years in every direction. Even the nearest galaxy would be unimaginably far away. For comparison, the Andromeda Galaxy, the closest major galaxy to the Milky Way, is a little more than 2 million light-years away. That distance already seems massive, but inside the Bhuta's void, the nearest neighbour could be dozens of millions or hundreds of millions of light-years distant. The concept of such loneliness on a cosmic scale is almost unsettling. Humans are accustomed to thinking of space as empty, but even the emptiness of our solar system is filled with planets, asteroids, comets, dust, and the light of the sun. The emptiness between stars contains gas, particles, and interstellar radiation. Yet a void like the Bhuta's void goes far beyond that. It is an expanse where entire galaxies are scarce, where the universe's grand structures fall away, leaving only a faint whisper of stars scattered along thin strands of matter. The scale pushes the limits of what people can comfortably imagine. Studying such regions provides clues about how the early universe expanded and how large-scale structures grew over billions of years. The Bhuta's void is part of a much larger cosmic landscape. Many voids fill the universe, creating a kind of sponge-like or web-like pattern. Dense regions form clusters and superclusters, while empty zones form between them. When a void reaches a certain size, it begins to influence the motion of galaxies around it. Gravity from surrounding structures pulls matter away from the interior of the void, making the empty region grow even larger over time. This process slows down only when the remaining material is spread so thin that its gravitational pull becomes extremely weak. The Bhuta's void offers a perfect example of this process at the extreme end of scale. Observing how galaxies move around its edges can help scientists measure the strength and influence of dark energy. Dark energy is the mysterious force that causes the universe to expand at an accelerating rate. Because voids are low-density regions, dark energy often has a stronger relative effect inside them, stretching space within the void more quickly than in nearby dense regions. Studying the expansion around and within the Bhuta's void gives astronomers valuable data about how dark energy behaves across different cosmic environments. Even the void's shape is of interest. Although often described as roughly spherical, it is not perfectly so. Most voids have irregular shapes because they grow unevenly, depending on how surrounding matter flows and moves. The Bhuta's void, however, is fairly round compared to many others. This shape suggests that the merging of smaller voids happened in a way that produced a fairly symmetric structure. Such symmetry indicates that the distribution of matter around the void may have been somewhat uniform over long periods of time, giving researchers insight into the early stages of cosmic evolution. Astronomers continue to study this region using modern instruments, including powerful space telescopes and advanced simulations run on supercomputers. Each new observation enhances the understanding of how such an enormous emptiness could arise naturally. While the Bhuta's void is not the only large void in the universe, its size makes it one of the most remarkable. It is a reminder that the universe is far from uniform, and that even on the largest scales, enormous differences can appear, depending on how matter clustered in the early moments after the Big Bang. The Bhuta's void also offers a humbling perspective. On Earth, the concept of emptiness usually refers to a room without furniture, or a silent field without buildings. In space, emptiness often refers to areas without stars or planets. But a supervoid forces the mind to consider emptiness on a scale so massive that entire galaxies become rare objects drifting within an unimaginable desolation. In such a place, even the greatest cosmic structures, galaxies themselves, seem fragile and small. The Great Nothing, as some call it, therefore represents more than a scientific curiosity. It stands as a testament to the vast, uneven, and deeply mysterious nature of the universe. It shows how cosmic evolution can produce regions overflowing with galaxies and others nearly devoid of them. It reflects the early universe's subtle patterns and amplifies them into giant structures that stretch across hundreds of millions of light years. And within this unimaginable gulf lie a few lonely galaxies, drifting through a darkness so deep and so quiet that their light must travel for hundreds of millions of years before reaching any observers capable of noticing them. The local void is one of the most astonishing and perplexing features in the nearby universe. A colossal expanse of space almost entirely empty of galaxies, lying just next to the cluster of galaxies that includes our own Milky Way, known as the local group. This vast emptiness was first noticed and formally documented in the year 1987 by astronomers Brent Tully and Rick Fisher, whose careful mapping of the motions and locations of nearby galaxies revealed an area of space that seemed almost entirely devoid of the familiar clumps, chains, and clusters of galaxies that populate the cosmos. Since that discovery, our understanding of the local void has grown more detailed, showing that it is not simply a single empty region, but rather composed of three separate sectors, each divided by delicate bridges of extremely faint cosmic material, often called wispy filaments, which hint at a tenuous structure even within the emptiness. The exact boundaries and full extent of the local void remain uncertain, largely because measuring the dimensions of an empty space is intrinsically difficult when there is so little matter to mark its edges. Observations suggest that it stretches at least 45 megaparsecs across, which translates into a staggering 150 million light-years, a distance so enormous that light itself would take 150 million years to cross from one side to the other. Some estimates place the void's total size much larger, perhaps extending up to 150 or even 300 megaparsecs, meaning it could span nearly 500 million to a billion light-years in total width. Its enormous size alone challenges our ability to grasp it intuitively, as it dwarfs familiar cosmic landmarks, dwarfing even entire clusters of galaxies that might contain thousands of members. What makes the local void even more fascinating is that, compared to predictions from standard cosmology, it appears to have far fewer galaxies than scientists would expect to find in such a region. This extreme sparsity has led to intense curiosity and debate about the processes that could create such a massive emptiness in the universe. Cosmic voids like this one do not appear randomly, but are shaped by the same gravitational forces that structure the rest of the universe. Gravity causes matter to cluster together, forming dense regions filled with galaxies, while other areas become more empty as matter is pulled toward these concentrations. These clusters, chains, and sheets of galaxies define the cosmic web, leaving vast gaps, voids, in between. Yet the precise way in which these voids form, expand, and interact with their surroundings is still not fully understood. Some theories suggest that voids result naturally from the growth of matter under gravity, while others propose that additional forces, possibly related to dark energy, might play a significant role. Even the seemingly simple question of why the local void contains so few galaxies compared to what models predict remains a matter of scientific discussion. Our own galaxy, the Milky Way, resides in a surprisingly significant location relative to the local void. It lies within a relatively flat and extended collection of galaxies known as the local sheet, which forms one of the boundaries of this vast emptiness. The local void begins at the edge of the local group, stretching outward for about 60 megaparsecs, which is roughly 200 million light-years. The distance from the Earth to the center of this void is believed to be at least 23 megaparsecs, about 75 million light-years, placing us relatively close to its heart. This proximity has profound effects, as the presence of such an enormous underdense region influences the motion of galaxies nearby, including our own. Astronomers have been able to estimate the size and properties of the local void in part through the study of an isolated dwarf galaxy called ESO 461-36, which exists within its bounds. Dwarf galaxies are small, faint, and generally less gravitationally bound than larger galaxies, making them sensitive indicators of their environment. In theory, a galaxy inside a void, where the gravitational pull of surrounding matter is weak, should move away more quickly from the emptiness toward regions with greater concentrations of matter. Observations confirm that ESO 461-36 is indeed moving outward, but the speed at which it is being expelled from the void appears higher than what would be expected from the gravitational effects of the surrounding matter alone. This anomaly has opened the door to alternative explanations, including the possible influence of dark energy, a mysterious form of energy that seems to permeate space and drive the accelerated expansion of the universe. The local void thus becomes not only a test case for our understanding of galaxy motions, but also a laboratory for exploring the subtle interplay between gravity, cosmic expansion, and dark energy. In the past, astronomers considered a related model known as the Hubble bubble, which was based on measuring the velocities of a specific type of exploding star called Type 1 supernovae. These supernovae serve as standard candles, allowing scientists to determine distances and relative motions in the universe. Early data suggested the possibility of a relative void centered on the Milky Way, where the local universe might be slightly emptier than surrounding regions. However, subsequent analyses revealed that the initial observations had been influenced by interstellar dust, which absorbed and scattered light, creating misleading measurements. Correcting for these effects has refined our understanding of local cosmic emptiness and reinforced the significance of the local void, even as debates continue about its precise influence. Observational studies extending outward from the Milky Way up to about 300 megaparsecs show that the local universe is indeed underdense compared to neighbouring regions. The density of galaxies and matter within this area is between 15 and 50% lower than what is typical elsewhere, giving rise to terms such as the local void or local hole. Some media outlets have referred to this feature as the KBC void, named in part after the initials of key researchers, though this nomenclature has not been universally adopted within the scientific literature. Regardless of its label, the implication is clear. The region of space in our immediate neighbourhood is extraordinarily less crowded than the cosmic average, a reality with tangible consequences for the motion of galaxies and the overall structure of the universe around us. One of the most remarkable aspects of the local void is that it is actively growing. Observations indicate that the local sheet, which forms one of the walls of the void, is moving away from the void's centre at a staggering speed of 260 kilometers per second, or roughly 160 miles per second. This movement is a direct consequence of the void's low density. As matter clumps in surrounding regions, it effectively pulls galaxies and sheets of galaxies away from the emptier area, causing the void to expand over time. The expansion is not uniform, however, because while most directions around the void are filled with matter, one sector appears almost completely empty. This asymmetry leads to an enhanced effect, accelerating the movement of galaxies away from the emptier region. The influence of the local void on our own galaxy is dramatic. The Milky Way is moving away from the centre of the local void at a speed of 970,000 kilometers per hour, or 600,000 miles per hour. This motion is not merely an abstract measurement. It reflects the tangible gravitational dynamics at play in our cosmic neighbourhood. The emptiness of the local void effectively pushes galaxies like ours outward, while the surrounding denser regions pull matter toward themselves. It is a stunning illustration of how even the absence of matter can exert a powerful effect on the universe, shaping motions on a scale far beyond ordinary human experience. The study of the local void has far-reaching implications beyond simply cataloguing empty space. It challenges astronomers to refine models of cosmic structure formation, to reconcile observed galaxy motions with theoretical predictions, and to consider the roles of dark energy and other unknown forces in shaping the large-scale universe. The peculiar dynamics of dwarf galaxies such as ESO 461-36, the measurable velocity of the local sheet, and the extraordinary speed of the Milky Way itself all point toward a universe in which emptiness is not a void of influence, but a region with measurable, significant effects on everything around it. The emptiness of the local void is not merely a passive absence of stars and galaxies, it is an active, dynamic participant in the cosmic ballet, exerting forces, influencing motions, and expanding over time in ways that continue to puzzle and inspire astronomers. Researchers continue to explore the local void through multiple avenues, including mapping the positions of faint galaxies, measuring the cosmic microwave background radiation, and analysing the flow of matter on both small and large scales. The behaviour of galaxies in and around the void helps constrain models of dark matter distribution, gravitational dynamics, and the influence of dark energy. By studying these vast empty regions, scientists gain insight into the very processes that have sculpted the cosmic web over billions of years, revealing a universe in which the interplay of presence and absence, of mass and emptiness, drives evolution on incomprehensibly large scales. The local void structure, with its three distinct sectors and thin filaments connecting them, also offers a rare glimpse into the ways matter can organize itself, even in the most sparse environments. These filaments, barely detectable against the near-perfect blackness of the surrounding void, hint at the lingering presence of gravitational connections, threads of material that survive the general evacuation of galaxies. Observations suggest that these wispy structures may serve as channels along which matter can slowly migrate, potentially seeding future galaxies or influencing the paths of nearby objects. The mere existence of these faint bridges suggests that even in extreme emptiness, the universe is never entirely static. It continues to evolve, reorganize, and interact over timescales measured in billions of years. The local void also provides a unique laboratory for examining competing cosmological theories. Standard models based on cold dark matter and ordinary gravitational physics predict certain rates at which galaxies should evacuate voids, yet the behavior of ESO 461-36 and other nearby dwarfs shows that reality may be more complex. The unexpectedly high speed of motion away from the void has prompted researchers to consider additional influences, including the potential role of dark energy or modifications to conventional gravitational theory. By comparing the observed motions with model predictions, scientists hope to refine our understanding of both the large-scale structure of the universe and the fundamental forces that govern it. Moreover, the local void challenges our perception of the universe as uniform on smaller scales. While the cosmological principle asserts that the universe is homogeneous and isotropic when viewed at very large scales, the existence of enormous underdense regions such as this one reminds us that on scales of hundreds of millions of light-years, dramatic variations in density exist. These variations influence not only the motion of individual galaxies, but also the growth of structures, the propagation of gravitational waves, and potentially the expansion rate of the universe itself. Understanding these local deviations is essential for interpreting observations of more distant regions, and for connecting our local cosmic environment to the broader story of the universe's evolution. Even the human perspective on our place in the universe is subtly affected by the local void. Knowing that our galaxy exists on the edge of a vast emptiness, rather than in a typical evenly populated region, highlights the unevenness of cosmic structures. It underscores the fact that what we observe nearby may not represent the average conditions in the universe, a consideration that becomes critical when using local measurements to infer universal constants or to test cosmological models. The local void reminds us that emptiness, far from being irrelevant, plays a significant role in shaping the behavior of galaxies, the flow of matter, and the unfolding of cosmic history. Mapping the local void remains an ongoing challenge. Astronomers employ a combination of observational strategies, including detailed redshift surveys, studies of galaxy peculiar velocities, and measurements of background radiation. Each of these approaches contributes pieces to a puzzle that spans hundreds of millions of light-years, revealing the void's size, shape, and dynamics. The interplay between the void and surrounding matter is intricate. The void is not a simple sphere of nothingness, but a dynamic, evolving region, whose boundaries shift and whose contents, while sparse, can still inform us about the physics governing the cosmos. In addition to influencing galaxy motions, the local void may play a role in other cosmic phenomena. Its presence affects the gravitational potential in our region of space, which in turn can influence the trajectories of intergalactic gas, the formation of new stars in nearby galaxies, and even the propagation of cosmic radiation. The interplay between void and matter illustrates a delicate balance in which empty regions are not mere gaps, but active participants in the cosmic landscape, exerting forces, guiding flows, and shaping structures over billions of years. The ongoing study of ESO 461-36 and other void-dwelling galaxies continues to yield surprises. Their rapid motion away from the void's center has prompted renewed consideration of alternative physics, including possible variations in the strength of gravity over vast distances or previously unaccounted for interactions with dark energy. These studies exemplify how even a single dwarf galaxy in a sparsely populated region can inform our understanding of the larger scales of the universe, providing clues about both local dynamics and the broader cosmic framework. Through detailed observation, modeling, and simulation, scientists aim to reconcile the apparent emptiness of the local void with the broader structure of the cosmic web. The void's three sectors, its connecting filaments, and its asymmetric distribution of surrounding matter offer a laboratory unlike any other, revealing the interplay of gravity, motion, and expansion in a nearly pristine environment. The lessons learned from the local void extend far beyond its immediate vicinity, providing insights into the formation of cosmic structures, the influence of dark energy, and the processes that drive the evolution of galaxies over billions of years. The local void demonstrates that emptiness itself is an essential component of the universe's architecture. Its effects on the local sheet, the Milky Way, and dwarf galaxies such as ESO 461-36 illustrate how even regions lacking in visible matter exert profound influence on the dynamics of the cosmos. The void's continued expansion, the speed at which matter is being drawn away from it, and the unusual motions observed within it challenge astronomers to rethink traditional notions of gravity, density, and cosmic evolution. Each new measurement, observation, and analysis deepens our understanding while revealing new questions about how such enormous empty spaces can coexist with the densely packed clusters, chains, and filaments that make up the rest of the universe. The detailed mapping of the local void, the study of its structural filaments, and the careful measurement of galaxy velocities together form a picture of a dynamic and evolving region where emptiness exerts as much influence as matter. The dwarf galaxy ESO 461-36, by moving rapidly out of the void, serves as a tangible indicator of the underlying forces at work, a living probe in a region otherwise devoid of life. The local sheet, racing away at hundreds of kilometers per second, highlights the large-scale consequences of an underdense region in the cosmic web. The Milky Way itself is caught in this motion, reminding us that even our galaxy, familiar and seemingly stable, is subject to the vast invisible currents of the universe. The local void's three sectors, the empty sector that accelerates matter outward, and the filaments that hint at residual structure together, paint a picture of cosmic evolution in action. These features demonstrate that even regions largely lacking in matter are complex, dynamic, and critical to the overall architecture of the universe. Studying them provides insights into galaxy formation, the behavior of dark energy, and the large-scale motion of cosmic structures. As scientists continue to probe the void, each observation adds to an intricate and growing understanding of how emptiness shapes the cosmos on scales far beyond human comprehension. Even beyond the immediate vicinity of the local void, its presence influences our broader view of the universe. By observing how galaxies move in response to underdense regions, astronomers can refine models of large-scale structure, test theories of gravity, and explore the properties of dark energy. The void acts as a natural laboratory in which the absence of matter becomes a tool for understanding the presence of forces that otherwise remain invisible. Its study exemplifies the profound ways in which emptiness and structure interact, shaping the motions of galaxies, the growth of cosmic filaments, and the distribution of matter across millions of light-years. The local void remains a focus of intense study not only because of its size and emptiness, but also because of its dynamic influence on nearby galaxies and structures. Its ongoing expansion, the speed of the local sheet, and the rapid motion of ESO 461-36 challenge our understanding of the universe's behavior on local scales. Each measurement reveals new complexities, including asymmetries in matter distribution, subtle influences of dark energy, and the intricate motions that arise when gravity interacts with large-scale emptiness. The Milky Way's speed of 970,000 km per hour away from the void's center is a striking reminder that our galaxy is not a static observer in space, but an active participant in a complex, evolving universe. The local void, through its emptiness, effectively shapes the environment in which our solar system resides, influencing the paths of nearby galaxies and altering the gravitational landscape over hundreds of millions of light-years. The void's presence has implications not only for local dynamics, but also for interpreting observations of more distant cosmic phenomena, linking the immediate cosmic neighborhood to the broader universe in profound ways. By examining the local void, astronomers gain insight into the fundamental processes that govern galaxy motion, cosmic expansion, and the evolution of large-scale structure. Its vast emptiness, dynamic filaments, and interacting walls create a natural laboratory in which the interplay of gravity, dark energy, and motion can be observed on scales impossible to reproduce on Earth. The study of such voids challenges assumptions, refines theories, and provides a window into the processes shaping the universe over billions of years. The local void illustrates that emptiness is far from inert. It drives motion, influences the formation and movement of galaxies, and shapes the expansion of surrounding structures. Its three sectors, thin connecting filaments, and one particularly empty sector, demonstrate that even regions that appear devoid of matter are sites of intense cosmic activity and influence. The dynamics of the local void, including the accelerated motion of dwarf galaxies and the large-scale movement of the Milky Way and local sheet, continue to provide valuable insights into the underlying physics of the universe. This enormous, underdense region of space highlights how voids play a crucial role in the cosmic web, guiding matter, influencing velocities, and shaping the distribution of galaxies. The local void's growth, its influence on the Milky Way, and its impact on nearby dwarf galaxies reveal that emptiness is not simply a passive absence, but an active participant in the ongoing evolution of the universe. Its study offers a rare glimpse into the forces shaping large-scale structure, the behavior of dark energy, and the complex interactions between matter and space in regions of extreme emptiness. The dwarf galaxy ESO 461-36, the movement of the local sheet, and the Milky Way's rapid speed away from the void's center provide measurable evidence of the void's profound effects. These observations are crucial in testing cosmological models, refining our understanding of gravitational dynamics, and exploring the influence of underdense regions on galaxy motion. The local void, with its enormous size, dynamic structure, and measurable impact, remains a compelling focus of research, demonstrating that the emptiest regions of the universe can have the most significant influence on the surrounding cosmic environment. The study of the local void, including its three sectors, its isolated dwarf galaxies, and its influence on surrounding structures, continues to deepen our understanding of how large-scale cosmic emptiness interacts with matter, shapes galaxy motion, and contributes to the ongoing evolution of the universe. Through careful observation and modelling, astronomers are uncovering the ways in which this seemingly empty region actively participates in the cosmic narrative, driving motion, influencing the distribution of galaxies, and offering insights into the fundamental workings of the universe. The local void demonstrates that even spaces that appear completely empty can have enormous gravitational and dynamical consequences, influencing nearby galaxies in ways that are measurable and astonishing. Its emptiness is not simply a lack of matter, but a defining factor in the motion of galaxies, including our own Milky Way, and in the expansion and structuring of the surrounding cosmic web. The local sheet, which forms one of the walls of the local void, illustrates how galaxies congregate around underdense regions. Its movement away from the void's center at 260 km per second is a direct consequence of the gravitational imbalance between dense matter concentrations and the emptiness of the void itself. This speed, while extraordinary in human terms, is a normal part of the cosmic dynamics dictated by the interplay of gravity and the large-scale distribution of matter. In essence, the local void acts as a gravitational complement. While clusters pull matter inward, voids facilitate outward motion, creating a cosmic push-pull that shapes the velocities and trajectories of galaxies. The dwarf galaxy ESO 461-36 continues to serve as a key indicator of the local void's influence. Observations of this small, isolated galaxy reveal that it is being expelled from the void faster than would be expected from gravitational effects alone. This discrepancy has led scientists to consider additional phenomena, such as the influence of dark energy, which may contribute to the galaxy's unexpectedly rapid motion. The study of ESO 461-36 thus exemplifies the broader importance of voids as laboratories for testing fundamental physics. By examining the behavior of such galaxies in extreme underdense environments, astronomers gain insight into forces that operate on scales far beyond the reach of terrestrial experiments. The shape of the local void, with its three distinct sectors and wispy filaments connecting them, suggests that even regions considered empty are never entirely uniform. These filaments, composed of sparse gas and residual matter, indicate that matter has a tendency to remain connected even under conditions of extreme rarity. They serve as traces of the cosmic web within the void, hinting at pathways along which matter can migrate over billions of years. While the vast majority of the void is almost completely empty, these filaments reveal subtle, persistent structures that play a role in the gradual redistribution of matter across cosmic distances. The ongoing expansion of the local void is another remarkable feature. As surrounding matter clumps into sheets, clusters, and filaments, the void itself grows larger. This expansion is not a passive process, but an active redistribution of matter, as galaxies are effectively pushed away from the emptiest regions. The asymmetry in the void's distribution, with one sector almost completely devoid of matter, amplifies this effect, accelerating the outward motion of galaxies along the most underdense pathways. This dynamic is observed not only in small, isolated galaxies, but also in larger structures, including the Milky Way itself. The Milky Way's rapid motion away from the local void at 970,000 km per hour provides a striking demonstration of the void's influence. This movement is not random, but a response to the gravitational imbalance created by the void's emptiness in one sector and the relative concentration of matter in surrounding regions. It highlights the interconnected nature of the universe. Even vast, empty regions can drive motion on scales that affect the trajectories of entire galaxies. The Milky Way, though massive and gravitationally dominant within the local group, is nevertheless subject to the subtle but powerful effects of underdense regions nearby. Studies of the local void also provide insight into the broader behavior of cosmic voids throughout the universe. Observations indicate that voids are not static. They expand over time, interact with surrounding matter, and influence the motion of galaxies over millions or billions of years. By examining the local void, astronomers can test models of void formation, the effects of dark energy, and the redistribution of matter across cosmic scales. The peculiar motions of galaxies within and near the void serve as natural probes, allowing scientists to measure gravitational forces, velocities, and the influence of both visible and invisible forms of matter. The local void's extreme emptiness, combined with its structural complexity, makes it a natural laboratory for understanding the cosmic web. Its three sectors, thin filaments, and asymmetric matter distribution provide clues about how voids interact with the larger-scale universe. Even in the absence of dense clusters, gravitational forces shape the motion of galaxies, causing flows of matter that can be measured and compared with theoretical predictions. The rapid motion of ESO 461-36, the outward push on the local sheet, and the Milky Way's velocity collectively reveal the dynamic nature of this void, illustrating how emptiness can be as influential as matter in the cosmic story. The local void also challenges astronomers to refine their measurements and theoretical models. The presence of underdense regions complicates attempts to determine cosmic parameters, such as the Hubble constant, because local variations in density affect observed galaxy velocities. By studying voids like this one, scientists can better understand the local deviations from average cosmic expansion and improve models that link nearby observations to the universe's large-scale behavior. The void's influence extends beyond immediate surroundings, affecting interpretations of distant galaxy surveys and contributing to a more accurate understanding of the universe's structure and evolution. Moreover, the local void provides a striking example of the relationship between emptiness and motion in the cosmos. While we often think of gravity as a force that pulls objects together, the dynamics of voids reveal a complementary aspect. Areas of extreme emptiness effectively create a repulsive-like effect, causing galaxies to move away from underdense regions toward denser surroundings. This motion is not caused by an actual repulsive force, but by the imbalance of gravitational attraction in the presence of voids. The Milky Way's movement away from the local void, the acceleration of the local sheet, and the escape trajectory of ESO 461-36 all exemplify this principle, demonstrating that voids play an active role in shaping galactic motion. The study of the local void continues to reveal new details about the distribution of matter on large scales. Surveys of galaxy redshifts, measurements of peculiar velocities, and mapping of faint filaments all contribute to a more complete picture of this extraordinary region. Even subtle features such as the shape of filaments or the slight density variations within sectors provide valuable information about the history and evolution of the void. These details are essential for understanding how voids form, expand, and influence the surrounding cosmic web, offering insights into both local and universal processes. Scientists also consider the local void when examining the role of dark energy in cosmic evolution. The unexpectedly rapid motion of galaxies away from the void suggests that there may be forces at work beyond standard gravitational effects. Dark energy, which drives the accelerated expansion of the universe, could contribute to these motions, though its precise influence remains a subject of ongoing research. The combination of observations, theoretical models, and simulations allows astronomers to explore how voids like this one provide natural laboratories for studying the interaction between visible matter, and dark energy. The local void's influence on the Milky Way and nearby structures also underscores the importance of location within the universe. Galaxies residing near voids experience different gravitational environments than those embedded within dense clusters. These variations affect not only motions, but also the evolution of galaxies themselves, influencing star formation rates, gas distribution, and interactions with neighboring galaxies. The local void, by providing a relatively underdense environment, shapes the dynamics and evolution of the local sheet, the Milky Way, and dwarf galaxies in a way that is both subtle and profound. Mapping the local void remains a complex task, requiring careful observation and analysis. Astronomers combine multiple techniques, including redshift surveys, studies of galaxy velocities, and measurements of cosmic background radiation to construct an accurate three-dimensional picture. Each new observation refines our understanding of the void's size, shape, and influence, revealing the intricate interplay between emptiness and matter. Even though the void is largely devoid of galaxies, the few objects within or near it serve as traces of its structure and dynamics, providing measurable evidence of its powerful effects. The local void also emphasizes the importance of scale in understanding the universe. While the cosmological principle posits that the universe is homogeneous and isotropic on the larger scales, the existence of vast underdense regions demonstrates that local variations in density are substantial. These variations affect galaxy motions, the growth of large-scale structures, and the interpretation of cosmological observations. Studying the local void, therefore, provides critical insight into how the universe behaves on scales where density fluctuations become significant, bridging the gap between local observations and universal trends. Even the faintest filaments within the local void hint at the persistent presence of structure in the universe. These wispy connections may channel matter, influence galaxy trajectories, and provide clues about the history of the void's formation. The fact that such delicate features exist within a region, otherwise nearly empty, underscores the complexity of cosmic evolution and the resilience of matter in responding to gravitational forces, even under extreme conditions. By studying these filaments, astronomers can better understand the processes that govern matter redistribution across cosmic voids and the interaction between underdense and overdense regions. The local void continues to challenge and inspire astronomers by demonstrating that emptiness is far from insignificant. Its dynamic effects on nearby galaxies, its role in shaping the local sheet, and its influence on the Milky Way's motion reveal that even regions largely devoid of matter exert profound forces on their surroundings. The study of this enormous void provides insight into fundamental processes, including gravitational dynamics, the behavior of dark energy, and the evolution of large-scale structure. By observing the motions of galaxies within and around the void, scientists can refine models of cosmic expansion, test theories of gravity, and explore the intricate interplay between matter and emptiness across hundreds of millions of light-years. The local void's three sectors, the isolated dwarf galaxies within it, and the wispy filaments connecting them illustrate a complex and evolving system. Despite its apparent emptiness, the void actively shapes the motion of galaxies, redistributes matter, and influences the growth of structures on scales far beyond human comprehension. ESO 461-36, the local sheet, and the Milky Way serve as living indicators of the void's influence, providing measurable evidence of the gravitational dynamics at work. By studying these effects, astronomers gain insight into both the local universe and the broader cosmic web, revealing the fundamental principles that govern the evolution of the cosmos over billions of years. The local void also offers perspective on the relationship between density and motion in the universe. While clusters and filaments attract matter through gravity, voids facilitate outward motion, creating a dynamic environment where galaxies are constantly responding to differences in density. The rapid velocities observed in the local sheet, the Milky Way, and dwarf galaxies such as ESO 461-36 highlight this principle, illustrating how emptiness can drive motion and shape the large-scale structure of the universe. This immense, underdense region underscores the significance of voids as active participants in cosmic evolution. Its three sectors, asymmetric distribution and wispy filaments, provide a rare opportunity to study the forces that shape galaxies and structures in underdense environments. The local void's expansion, its effect on nearby galaxies, and its potential interaction with dark energy reveal the complex and ongoing processes that govern the universe. Through careful observation and modelling, astronomers continue to unravel the mysteries of this extraordinary void, demonstrating that even the emptiest regions have profound and measurable impacts on the cosmic landscape. The local void's continuing study, encompassing its structure, dynamics, and influence on nearby galaxies, remains a central focus of modern cosmology. By examining this extraordinary region, scientists gain insights into gravitational dynamics, the role of dark energy, the behavior of matter in underdense environments, and the evolution of large-scale cosmic structures. Its presence illustrates that emptiness is far from passive. It actively shapes the motion of galaxies, the expansion of surrounding structures, and the redistribution of matter across vast cosmic distances. The Milky Way's motion away from the local void, the local sheet's rapid acceleration, and the escape trajectory of ESO 461-36 all exemplify the void's dynamic influence. These observations provide measurable evidence of how underdense regions impact the universe, offering a window into processes that operate on scales far beyond ordinary human experience. By studying the local void, astronomers continue to explore the fundamental forces that govern cosmic structure, the interplay between matter and emptiness, and the ongoing evolution of the universe over billions of years. The local void, with its enormous size, three-sector structure, and wispy connecting filaments, serves as a testament to the power of emptiness in the cosmos. It demonstrates that even regions with very little visible matter can profoundly influence nearby galaxies, shape the motions of entire sheets of galaxies, and affect the dynamics of the Milky Way. Its study provides critical insights into the formation of large-scale structures, the behavior of dark energy, and the complex interplay between gravity, motion, and emptiness across cosmic distances. The ongoing analysis of the local void continues to refine our understanding of the universe. By examining galaxy motions, mapping filaments, and measuring the expansion of nearby structures, scientists are uncovering the mechanisms by which emptiness shapes the cosmos. The dwarf galaxy ESO 461-36, the accelerating local sheet, and the Milky Way's high velocity all offer concrete evidence of the void's profound influence, illustrating that even regions of extreme underdensity are active participants in the cosmic web. The local void's remarkable emptiness, combined with its dynamic influence on nearby galaxies and structures, underscores the critical role that voids play in the universe. Far from being empty space, these regions drive motion, shape the distribution of matter, and influence the evolution of galaxies over billions of years. Its study provides valuable insights into the nature of cosmic expansion, the behavior of dark energy, and the forces governing large-scale structure, revealing a universe in which emptiness and matter are equally vital in shaping the cosmos. The local void's continued expansion, its influence on the local sheet, the Milky Way, and dwarf galaxies like ESO 461-36, and its wispy connecting filaments together paint a picture of a dynamic, evolving, and influential region. Even in its apparent emptiness, the void actively drives motion, redistributes matter, and shapes the evolution of nearby galaxies. Its study illuminates the subtle and powerful ways in which underdense regions contribute to the ongoing evolution of the universe, providing insight into fundamental processes that operate on scales that are almost impossible to imagine. The local void, in all its complexity and vastness, stands as a profound example of how emptiness itself can be a major driver of cosmic dynamics. Its three-sector structure, asymmetrical distribution of matter, and wispy filaments illustrate that even regions nearly devoid of galaxies remain active, influencing motions, shaping structures, and interacting with surrounding matter in ways that are both measurable and extraordinary. The void's effects on the local sheet, the Milky Way, and dwarf galaxies provide tangible evidence of its power, demonstrating that in the universe, emptiness can be just as consequential as the presence of matter. The local void's remarkable emptiness and dynamic influence provide an unparalleled opportunity to study the interplay between matter, gravity, and dark energy. By observing the motions of galaxies like ESO 461-36, measuring the speed of the local sheet, and analyzing the Milky Way's velocity, scientists gain insight into the forces shaping the universe on scales of hundreds of millions of light-years. This understanding not only illuminates the behavior of nearby structures, but also informs broader cosmological models, helping to bridge local observations with the universe at large. The local void demonstrates that emptiness is not a passive feature, but an active participant in the cosmic web. Its three sectors, wispy filaments, and underdense nature create conditions that drive galaxy motion, shape the distribution of matter, and influence the evolution of surrounding structures. The outward movement of galaxies from the void, the acceleration of the local sheet, and the Milky Way's high-speed trajectory all exemplify the profound effects of underdense regions, revealing a universe in which emptiness and matter interact in intricate and significant ways. The study of the local void continues to provide insights into the fundamental processes governing cosmic evolution. Its structure, dynamics, and influence on nearby galaxies illustrate how underdense regions contribute to the large-scale architecture of the universe. By analyzing the motion of dwarf galaxies, measuring the acceleration of galaxy sheets, and observing the Milky Way's trajectory, astronomers are uncovering the hidden forces at work in regions of extreme emptiness. The local void thus stands as a compelling example of how even the sparsest parts of the universe can shape the motions and evolution of the cosmic web. The local void's enormous scale, dynamic sectors, and subtle structural filaments reveal that emptiness is a driving factor in cosmic evolution. Its influence on the Milky Way, the local sheet, and isolated dwarf galaxies highlights the significant role that underdense regions play in shaping galaxy motion and large-scale structure. Through ongoing study and observation, the local void continues to inform our understanding of gravitational dynamics, dark energy, and the complex interplay between matter and space, providing a window into the mechanisms that govern the universe on incomprehensibly large scales. The local void remains an extraordinary example of how vast empty regions can have measurable and profound effects on nearby cosmic structures. Its three sectors, wispy filaments, expanding boundaries, and influence on galaxy velocities illustrate the interplay between emptiness and matter. By studying the local void, astronomers gain insight into the evolution of the cosmic web, the behavior of underdense regions, and the forces that govern galaxy motion across hundreds of millions of light-years. The void's continued study promises to reveal further secrets about the dynamic universe in which we reside. The northern local supervoid is a vast, sparsely populated region in the universe, a true emptiness in the cosmic web where matter is strikingly scarce, and dense clusters of galaxies are largely absent. Unlike the familiar bustling regions of space filled with galaxy groups and clusters, this supervoid represents one of the most silent and desolate stretches of the nearby universe. Its emptiness is so remarkable that, despite the fact that it is relatively close in cosmic terms, it almost seems to be a hidden realm within the universe, largely overlooked until astronomers began mapping the distribution of galaxies in fine detail. The void lies in a space surrounded by some of the universe's more prominent structures. To one side there is the Virgo supercluster, a massive conglomeration of galaxies, including our own Milky Way and nearby clusters of stars and galaxies. To another side, the Coma supercluster stretches across hundreds of millions of light-years, hosting hundreds of thousands of galaxies in a dense and complex arrangement, while the Hercules supercluster lies farther beyond, an equally dense region filled with galaxies grouped into clusters. The northern local supervoid exists between these cosmic giants, creating an extraordinary contrast. Whereas superclusters are crowded neighborhoods teeming with galaxies of all shapes and sizes, the supervoid appears almost like a vast cosmic desert, a region where galaxies are few, isolated and faint. On the celestial map, the northern local supervoid occupies a significant portion of the sky, positioned between several well-known constellations. Bootes, Virgo, and Serpens Caput are its primary celestial markers, their familiar stars forming a backdrop against which this emptiness stretches. While the stars themselves are only the nearest beacons of light within our own galaxy, They serve as reference points for astronomers measuring the positions and extents of distant cosmic structures. In this region of space, the emptiness is interspersed with a scattering of small galaxies, most of which are spiral galaxies. These spirals, though few, are notable because they retain the familiar swirling disk structures seen in galaxies like our own Milky Way. There are also a handful of small galaxy clusters, but these are far less dense and prominent than those found in neighbouring superclusters. The galaxies that exist in this void are faint, almost ghostly in their isolation, struggling against the surrounding emptiness. Their scarcity divides the northern local supervoid into smaller voids, each stretching across tens to hundreds of millions of light-years. These subvoids are generally 3 to 10 times smaller than the supervoid itself, creating a patchwork of emptiness interspersed with the occasional faint galaxy. The divisions reveal a kind of cosmic fractal, where emptiness repeats at smaller scales, a pattern of near-nothingness that reflects the large-scale structure of the universe in miniature. The location of the supervoid center is precise, measured to lie approximately 61 megaparsecs away from our solar system. Translated into light-years, this distance is nearly 199 million light-years, a staggering expanse that emphasizes the scale at which cosmic voids exist. Its position is marked roughly at 15 hours in right ascension and 15 degrees in declination, coordinates that astronomers use to pinpoint celestial objects in the sky with incredible accuracy. The northern local supervoid's diameter is immense, stretching across 104 megaparsecs at its narrowest point, which is approximately 339 million light-years. To comprehend such dimensions, one can imagine the fact that light, travelling at nearly 300,000 kilometers per second, would take more than 300 million years to traverse this void from one end to the other. Within this colossal emptiness, the few galaxies that are present appear small and dim against the vast canvas of nothingness, their relative isolation creating environments that are strikingly different from the dense, interactive neighbourhoods of superclusters. These galaxies are often separated by tens of millions of light-years, and interactions between them are rare. Unlike galaxies in denser regions, which frequently collide, merge, and influence one another gravitationally, galaxies in the northern local supervoid evolve in solitude, their growth and morphology shaped largely by internal processes rather than external cosmic forces. Astronomers have found that the faint galaxies within the supervoid are not distributed evenly. Instead, they tend to be spread thinly, forming filaments or chains that weave through the emptiness like faint threads in a cosmic tapestry. These filaments serve as the skeletal framework of the void, marking the boundaries of even smaller voids nested within the larger one. It is as if the supervoid is not completely featureless, but rather composed of a network of subtle structures that give it shape and definition despite the overwhelming emptiness. The void substructures are themselves notable. Their sizes range widely, from tens to over 100 million light-years across, revealing a hierarchy of emptiness that mirrors the cosmic web's overall architecture. This phenomenon illustrates that even the emptiest regions of space are not entirely void of structure. Rather, they display a faint imprint of the large-scale processes that govern the distribution of matter in the universe. The presence of these tiny filaments and isolated galaxies also provides astronomers with essential clues about the forces shaping the universe, including the effects of dark matter and dark energy, which influence how matter clumps together and how voids expand over time. The northern local supervoid has played an important role in our understanding of cosmic evolution. Being the closest known supervoid, it offers astronomers a nearby laboratory to study the dynamics of emptiness and how galaxies behave in regions with extremely low matter density. Observing the galaxies within this void has revealed that they often display unusual characteristics compared to their counterparts in denser regions. For instance, some of these galaxies are less massive, with fewer stars, and often exhibit slower rates of star formation. The isolation of these galaxies also reduces the frequency of gravitational interactions that can trigger bursts of star formation, leading to slower overall evolution. Moreover, studying the distribution of these galaxies provides vital information about the underlying dark matter structure of the universe, since even in the absence of visible galaxies, dark matter continues to influence the motion of whatever matter is present. The void's proximity means astronomers can study its galaxies in greater detail than more distant voids, allowing for more precise measurements of their properties such as mass, rotation, gas content, and chemical composition. The northern local supervoid's relationship with surrounding structures is equally significant. Its borders are defined not just by the absence of galaxies, but also by the surrounding dense clusters of the Virgo, Coma, and Hercules superclusters. These massive structures exert gravitational influence over the void, shaping its boundaries and subtly affecting the motion of galaxies within it. The contrast between the dense superclusters and the emptiness of the void highlights the extreme variability in matter distribution across the universe. This juxtaposition provides insight into the processes that lead to the formation of the cosmic web, a vast network of matter that spans the observable universe. The formation of the northern local supervoid likely involved a combination of gravitational forces pulling matter into nearby superclusters and the expansion of space, which stretches voids and pushes galaxies further apart. Over billions of years, these processes would have amplified the emptiness of this region, creating the supervoid as it exists today. In mapping the void, astronomers have noted its complex structure. Though it appears largely empty, careful surveys using sensitive telescopes reveal faint galaxies scattered across its interior. These galaxies are predominantly spirals, a category known for their thin, rotating disks, spiral arms, and central bulges. Some may also be irregular in shape, lacking the well-defined features of spirals or ellipticals. Despite their small numbers, these galaxies are valuable markers for understanding the distribution of matter. Their positions help outline the subvoids within the larger supervoid, showing where emptiness gives way to faint pockets of galaxies. Interestingly, these galaxies are not randomly distributed. Their faint filaments trace the underlying gravitational scaffolding of the universe, reflecting how matter has clumped together over cosmic timescales. In essence, the northern local supervoid is a stage on which the quieter, subtler aspects of cosmic structure play out, away from the dramatic collisions and mergers seen in crowded superclusters. The void's influence extends beyond its immediate volume. Because it is so large, the northern local supervoid contributes to the overall expansion of space in its region. The reduced gravitational pull within the void, due to the scarcity of matter, allows space to expand slightly faster than in denser regions. This differential expansion can subtly affect the motion of galaxies on the outskirts of the void, influencing the larger-scale dynamics of the universe. Such effects are difficult to measure, but can be inferred through careful observation of galaxy velocities and the cosmic microwave background radiation, the faint afterglow of the Big Bang. The void acts as a kind of negative mass region, where the gravitational influence is weaker and the motion of galaxies is affected accordingly. Researchers studying these motions hope to gain a better understanding of dark energy, the mysterious force driving the accelerated expansion of the universe, as voids like the northern local supervoid amplify the effects of this expansion. The discovery of the northern local supervoid added an important piece to the puzzle of cosmic structure. Its proximity allowed astronomers to study voids more thoroughly, revealing the variety and complexity of these underdense regions. While superclusters showcase the universe's tendency to clump matter into dense formations, supervoids demonstrate that large-scale emptiness is an equally fundamental aspect of the cosmos. The northern local supervoid scale, roughly 339 million light-years across at its narrowest, emphasizes the enormous distances between galaxies in such regions and the isolation that defines their environment. Every faint galaxy within it serves as a solitary witness to the vast emptiness surrounding it, highlighting how differently galaxies evolve in isolation compared to crowded neighborhoods. Studies of these galaxies continue to inform theories of galaxy formation and evolution, providing a unique contrast to the processes observed in dense clusters. Even within the northern local supervoid, the hierarchy of emptiness is apparent. Smaller voids within the supervoid vary in size and shape, creating a complex patchwork of regions with slightly differing galaxy densities. This nested structure suggests that the cosmic web is intricate at every scale, with empty spaces existing within larger empty spaces, all shaped by gravitational forces and the expansion of the universe over billions of years. Such a fractal-like pattern is a hallmark of large-scale cosmic organization, where the larger structures are composed of smaller, self-similar units. Observations of these patterns offer critical insight into cosmology, allowing researchers to test predictions about the distribution of dark matter, the behavior of dark energy, and the formation of galaxies over cosmic time. Astronomers also study the chemical composition of the few galaxies within the void, analysing their stars and gas to understand how isolation impacts galactic evolution. Fewer interactions with other galaxies generally result in lower rates of star formation and slower enrichment of interstellar material with heavier elements. These galaxies can therefore appear chemically simpler than their counterparts in superclusters, offering a glimpse into more pristine cosmic environments. This provides a window into the early processes of galaxy formation, as these galaxies may preserve conditions that were more common in the universe billions of years ago. Observing their rotation, structure, and gas content also helps refine models of how galaxies develop in low-density regions, complementing studies in crowded regions to provide a complete picture of galactic evolution across all environments. The northern local supervoid continues to be an area of active study. Astronomers use a variety of observational tools, from optical telescopes to radio and infrared surveys, to detect faint galaxies and map the distribution of matter. Each new observation reveals more about the void's structure, the characteristics of its galaxies, and the role of underdense regions in cosmic dynamics. By comparing the northern local supervoid to more distant and larger voids, researchers can learn how voids vary in size, composition, and evolution, providing a comparative perspective that enriches our understanding of the universe as a whole. The ongoing study of this supervoid highlights how even regions that appear empty are full of information, waiting to be deciphered by careful observation and analysis. The northern local supervoid is also important for understanding the peculiar velocities of galaxies in our local universe. Galaxies in and around the void move not only due to the expansion of the universe, but also in response to the gravitational influence of nearby dense superclusters. These peculiar velocities are deviations from the smooth expansion, and mapping them helps astronomers understand the distribution of matter, both visible and dark. The void acts as a kind of cosmic backdrop, its emptiness allowing surrounding structures to pull more effectively on nearby galaxies, creating measurable flows that reveal the underlying gravitational landscape. By studying these motions, scientists gain insight into the invisible scaffolding of dark matter that shapes the large-scale structure of the universe. The northern local supervoid's size, approximately 104 megaparsecs across its narrowest part, emphasizes just how immense cosmic voids are, dwarfing even the largest galaxies and galaxy clusters. Its proximity, just 61 megaparsecs away, makes it the nearest supervoid to our galaxy, offering a unique opportunity for detailed study. The faint galaxies within it, though few and far between, serve as critical markers that reveal the void's substructure and provide a laboratory for understanding how matter behaves in extremely low-density environments. Through careful observation, astronomers can trace the intricate web of filaments, small voids, and isolated galaxies, uncovering the subtle architecture of one of the most silent regions of space. The existence of the northern local supervoid reinforces the idea that the universe is not uniform at all scales. While the cosmic microwave background and large-scale surveys show remarkable uniformity when viewed from extreme distances, the distribution of matter reveals stark contrasts at closer scales. Supervoids like the northern local supervoid punctuate the cosmic landscape, demonstrating the universe's patchwork nature, where dense clusters and empty voids coexist in a complex arrangement. Studying such regions provides a deeper appreciation of the diversity of cosmic environments and the processes that govern the formation, growth, and distribution of galaxies across billions of light-years. The supervoid's relationship to the constellations Bootes, Virgo, and Serpens Caput highlights how astronomers use familiar star patterns to anchor the positions of distant and otherwise invisible structures. These constellations, composed of stars within our own galaxy, serve as reference points, allowing scientists to communicate the location of the northern local supervoid with precision. Observing from Earth, astronomers can map the faint galaxies within the void relative to these constellations, building a detailed three-dimensional model of the local universe. These maps reveal the void's boundaries, its internal subvoids, and the distribution of the few galaxies that reside within it, providing essential data for understanding the dynamics of underdense regions and their interaction with surrounding dense superclusters. Even though the northern local supervoid is sparsely populated, its very emptiness has profound implications for cosmology. It serves as a natural laboratory for testing theories about dark matter and dark energy, the forces that dominate the universe's evolution on large scales. The void's low matter density means that the effects of dark energy on the expansion of space are more pronounced, while the gravitational influence of dark matter is weaker, allowing astronomers to isolate and study these phenomena more clearly than in crowded regions. Observations of how galaxies move and cluster within and around the void provide critical constraints on cosmological models, helping refine our understanding of the universe's history, composition, and ultimate fate. The Northern Local Supervoid Center, located approximately 61 megaparsecs away, provides a fixed point from which astronomers measure its expanse and position. With its diameter of 104 megaparsecs across the narrowest width, this region covers hundreds of millions of light-years, a staggering distance that dwarfs individual galaxies and clusters. Even small galaxies within this void are separated by tens of millions of light-years, emphasizing the vast isolation that defines the environment. Their faintness and sparse distribution contrast sharply with the dense populations in neighboring superclusters, providing an extraordinary example of the diversity of cosmic environments and the remarkable scales over which emptiness can extend. The subvoids within the Northern Local Supervoid reveal a nested hierarchy of emptiness. These smaller voids, 3 to 10 times smaller than the supervoid itself, demonstrate that voids are not monolithic but contain internal structure shaped by gravitational forces and cosmic expansion. The faint galaxies along the edges of these subvoids trace the underlying cosmic web, illustrating how matter organizes itself even in regions that are overwhelmingly empty. These patterns provide a window into the processes of large-scale structure formation, offering clues about the initial density fluctuations in the early universe that evolved into the complex network of clusters, filaments, and voids observed today. The Northern Local Supervoid also provides insight into galaxy formation in extreme environments. Galaxies residing here often exhibit slower rates of star formation, smaller masses, and less complex chemical compositions compared to those in denser regions. Their isolation reduces the likelihood of interactions, mergers, and other gravitational influences that accelerate galactic evolution elsewhere. Studying these galaxies helps astronomers understand how intrinsic processes drive galaxy growth in the absence of external pressures, shedding light on fundamental questions about the life cycle of galaxies and the factors that shape their observable properties. The faint filaments within the Northern Local Supervoid serve as the skeletal framework that delineates its structure. They mark the boundaries between smaller subvoids and provide a faint imprint of the gravitational forces that have shaped the distribution of matter. These filaments, though composed of very few galaxies, highlight the intricate architecture of the cosmic web and the repeating patterns of emptiness and matter that extend across the universe. Observing these structures allows astronomers to connect the study of local voids with the broader understanding of cosmic evolution, linking the properties of individual galaxies with the dynamics of the universe on the larger scales. In addition to its structural importance, the Northern Local Supervoid has implications for the study of cosmic flows and peculiar velocities. Galaxies at the edges of the void experience gravitational attraction toward neighboring superclusters, creating observable motions that deviate from the general expansion of the universe. Mapping these flows provides critical information about the distribution of both visible and dark matter, revealing how underdense and overdense regions interact gravitationally. By analyzing these motions, scientists gain insights into the large-scale behavior of the universe, testing models of dark matter, dark energy, and the processes governing cosmic expansion. The Northern Local Supervoid is a striking reminder that even regions that seem empty can offer profound insights into the universe. Its size, spanning hundreds of millions of light-years, its faint, isolated galaxies, and its internal hierarchy of subvoids all contribute to a deeper understanding of the cosmic web and the forces that shape the universe. Observing and studying this void continues to reveal new details about the distribution of matter, the behavior of galaxies in low-density environments, and the fundamental forces driving cosmic evolution. Its proximity and accessibility make it an invaluable resource for astronomers seeking to unravel the mysteries of the universe, providing a nearby example of emptiness on a truly monumental scale. The ongoing study of the Northern Local Supervoid exemplifies the intricate balance between emptiness and structure in the cosmos. Even in a region defined by its lack of dense galaxy clusters, patterns emerge, revealing the subtle organization of matter across vast distances. The faint galaxies scattered throughout the void, the smaller nested voids, and the delicate filaments connecting them all demonstrate that cosmic emptiness is far from featureless. Instead, it is a dynamic environment shaped by gravitational forces, cosmic expansion, and the complex interplay between visible and dark matter. Each new observation adds another layer of understanding, showing that the universe is a patchwork of dense and empty regions, each with its own unique characteristics and significance. A void galaxy is a type of galaxy that exists in one of the vast, mostly empty regions of the universe known as cosmological voids. These voids are enormous spaces where very few galaxies are found, in stark contrast to the dense and crowded regions of the cosmos where galaxies tend to cluster together in massive groups, walls, sheets, and filaments that define the large-scale structure of the universe. The universe, on a grand scale, resembles a cosmic web, with galaxies and clusters forming the threads and nodes, and voids forming the enormous, almost entirely empty gaps in between. Within these immense emptinesses, galaxies are exceedingly rare, making the ones that do exist highly intriguing and significant to the study of cosmic evolution. Most galaxies that are studied exist in the crowded parts of this web, the walls and filaments surrounding the voids, but void galaxies occupy a completely different environment, one where the density of matter is extremely low, and interactions with other galaxies are minimal. Many of these void galaxies are not entirely isolated, however. They often remain connected by tenuous, delicate structures, called void filaments or tendrils, which are much thinner and less massive than the filaments that weave the crowded regions of the universe together. These tendrils serve as faint cosmic highways connecting a small number of galaxies within the voids, forming subtle networks that can span millions of light years. Unlike the filaments in more crowded areas, which are often twisted, bent, and influenced by the gravitational pull of many surrounding galaxies, void filaments tend to be straighter. This straightness results from the relative absence of nearby galactic masses, which in denser regions distort the shape and direction of the filaments. While less massive, these void filaments are not entirely insignificant. In some cases, they are dense enough to host small clusters of galaxies, often referred to as poor galaxy clusters, where a handful of galaxies group together in the otherwise empty void. The galaxies found in these empty regions are thought to be among the most pristine examples of galactic evolution in the universe. Because they are largely isolated and interact with very few neighbouring galaxies, they are likely to have evolved in a simpler manner compared to galaxies in dense clusters, which frequently undergo mergers, collisions, and gravitational interactions that dramatically alter their structure and composition. Void galaxies may have formed almost entirely from pure intergalactic gas, without significant contamination from the enriched material produced by generations of star formation in more crowded environments. This purity makes them invaluable to astrophysicists who are trying to understand the natural processes of galaxy formation and evolution without the complicating effects of galactic interactions. Astrophysicists have theorized that the presence of void galaxies is closely linked to the gravitational dynamics of the universe on the larger scales. Large galactic filaments, which connect clusters and superclusters, are influenced by the immense gravitational pull of these dense regions. Over time, these filaments are drawn toward the massive superclusters, leaving behind the less dense areas, which expand to form cosmic voids. This gravitational migration of matter effectively empties these regions of most galaxies, causing enormous voids such as the famous Butter's void to grow in size. The Butter's void, for example, spans hundreds of millions of light-years across, making it one of the largest known voids in the universe. Within such voids, only a small number of galaxies remain, sometimes as relics of the earlier distribution of matter before the surrounding filaments were pulled away. Galaxies like the spiral galaxy MCG plus 01, ZUS 2, 50ST provide concrete examples of these remnants. They are thought to have been left behind as the surrounding filaments and matter migrated toward more massive structures in the cosmic web. Being relatively isolated, these galaxies offer a rare opportunity to study the intrinsic properties of galaxies without the complications of frequent interactions or mergers that are common in denser regions. Observations of such galaxies can reveal the natural formation of spiral arms, star clusters, and other galactic features in an environment largely unaffected by external forces. The very isolation of these void galaxies may result in slower rates of star formation compared to galaxies in dense clusters, as the inflow of new gas is limited and interactions with other galaxies, which can trigger bursts of star formation, are rare. Studies of void galaxies have revealed a wide variety of structures and forms, from small, irregular dwarf galaxies to more massive spiral galaxies. Their physical characteristics often differ from those found in crowded environments. Many void galaxies tend to be bluer in colour, indicating the presence of younger stars and ongoing star formation. This contrasts with galaxies in dense clusters, which are often redder, dominated by older stars, and exhibit less active star formation due to the depletion of gas and frequent galactic interactions that strip away star-forming material. The chemical composition of void galaxies also tends to be simpler, with fewer heavy elements compared to their clustered counterparts, reflecting a more straightforward evolutionary path where fewer generations of stars have contributed to the enrichment of the interstellar medium. Void galaxies are also fascinating in terms of their dynamics and motions. Because they exist in low-density environments, the gravitational influences they experience are weak and often dominated by the subtle effects of the surrounding void rather than by nearby massive galaxies. Their rotation curves, velocities, and overall motion through space can provide insights into dark matter distributions and the effects of large-scale cosmic expansion in regions of extreme emptiness. The study of void galaxies allows scientists to test theories of cosmology, particularly those related to the growth of structure in the universe and the distribution of dark matter and dark energy. Observing how galaxies behave when isolated from the dense cosmic web gives a baseline for understanding fundamental cosmic processes without the interference of complex environmental factors. In recent decades, surveys using large telescopes and advanced observational techniques have begun to reveal the hidden populations of void galaxies in unprecedented detail. Deep sky imaging and spectroscopy have allowed astronomers to detect faint galaxies within voids, study their compositions, and map the subtle filaments and tendrils that connect them. These observations have led to the discovery that voids, while extremely underpopulated, are not completely empty. Instead, they contain a delicate and intricate network of galaxies, filaments, and even small clusters that demonstrate the resilience of structure formation even in the most sparsely populated regions of the universe. The study of void galaxies has implications for understanding the fundamental nature of the universe. By examining galaxies in such isolated conditions, scientists can test models of galaxy formation and evolution in a relatively controlled cosmic laboratory. These galaxies serve as natural experiments, revealing how gas cooling, star formation, and other astrophysical processes operate in environments largely free from external disturbances. Comparing void galaxies to those in dense clusters allows astrophysicists to distinguish between the effects of internal processes and environmental factors, leading to a deeper understanding of the life cycles of galaxies. The isolation of void galaxies also raises questions about the early stages of the universe. If these galaxies formed from pure intergalactic gas, they may preserve a record of primordial conditions that is largely erased in galaxies that have undergone frequent mergers or interactions. Studying their chemical composition, stellar populations, and overall structure can provide clues about the distribution of matter shortly after the Big Bang and the subsequent evolution of the cosmic web. Void galaxies may act as time capsules, offering a glimpse into the simpler, less chaotic conditions of the early universe. Furthermore, the growth of voids and the behavior of galaxies within them are influenced by the same cosmic forces that shape the entire universe. Dark energy, which drives the accelerated expansion of the universe, plays a particularly important role in the dynamics of voids. As space expands, voids tend to grow larger, and galaxies within them become even more isolated. The interplay between the expansion of voids, the gravitational pull of surrounding superclusters, and the motion of galaxies within tendrils and filaments creates a complex but fascinating picture of cosmic evolution. Void galaxies also provide a unique opportunity to study star formation in extreme conditions. In dense environments, interactions between galaxies, such as mergers and tidal forces, often trigger bursts of star formation. In contrast, void galaxies evolve in relative solitude, and their star formation is largely governed by the availability of intergalactic gas and the internal dynamics of the galaxy itself. This allows astronomers to study the natural progression of star formation and the growth of stellar populations without external triggers, shedding light on the intrinsic processes that drive the evolution of galaxies over billions of years. Some void galaxies are remarkably large and well-formed despite their isolation. challenging previous assumptions that galaxies in empty regions would necessarily be small and underdeveloped. The presence of well-defined spiral structures and active star-forming regions in such galaxies suggests that galactic evolution can proceed efficiently even in low-density environments. These findings underscore the importance of internal processes, such as the rotation of gas and the influence of dark matter halos, in shaping galaxies independently of their surroundings. The study of void filaments and tendrils connecting galaxies within voids has revealed that even in the emptiest regions of the universe, matter tends to organize itself into coherent structures. These filaments act as conduits for the flow of gas, and occasionally for the formation of small groups of galaxies. While these structures are thinner and less massive than those in dense regions, they nevertheless demonstrate the universality of gravitational processes in shaping the distribution of matter on all scales. The discovery of these structures has also highlighted the need to refine models of large-scale cosmic structure, accounting for the subtle but important interactions within voids. Void galaxies often exhibit slower chemical evolution compared to their clustered counterparts. With fewer supernovae and lower rates of star formation, the enrichment of the interstellar medium with heavy elements occurs more slowly, resulting in galaxies that retain a more primordial composition. This makes void galaxies valuable targets for spectroscopic studies, as their elemental abundances can provide insights into the early chemical conditions of the universe. By comparing these galaxies to those in dense clusters, scientists can trace the impact of environment on chemical evolution and better understand the timeline of element formation throughout cosmic history. The kinematics of void galaxies, how they move and rotate, also provide important clues about the underlying distribution of dark matter. In dense regions, galaxy motions are heavily influenced by the gravitational pull of surrounding masses, making it difficult to isolate the effects of dark matter halos. In contrast, the relative isolation of void galaxies allows researchers to observe their motions in environments minimally influenced by external forces, providing cleaner data for testing models of dark matter distribution and its role in shaping galaxies. Over time, the study of void galaxies has expanded to include their potential interactions with the cosmic microwave background and large-scale structure formation. By analyzing the distribution and properties of these galaxies, astronomers can gain insights into how voids affect the propagation of light, the growth of structure, and the dynamics of cosmic expansion. The voids themselves, along with their galaxies, are integral components of the cosmic landscape, influencing the flow of matter and energy across the universe in subtle but measurable ways. In recent years, computer simulations of cosmic structure formation have been used to model voids and their galaxies in unprecedented detail. These simulations show how large-scale gravitational processes can evacuate regions of space, leaving behind isolated galaxies connected by delicate filaments. They also predict the existence of void galaxies with characteristics similar to those observed, providing a theoretical framework that supports observational findings. These models have become essential tools for understanding the complex interplay between gravity, dark matter, and cosmic expansion in shaping the distribution of galaxies across the universe. Observations have revealed that void galaxies are not randomly distributed within voids. Instead, they follow subtle patterns, often aligning along filaments and tendrils that connect them to the wider cosmic web. This suggests that even in the emptiest regions, gravitational forces still guide the distribution of matter, creating an organized structure on scales that are otherwise almost incomprehensibly vast. The fact that galaxies remain connected, even sparsely, highlights the persistent influence of gravity in shaping the universe, regardless of local density. In addition, void galaxies can provide insights into the effects of cosmic isolation on the growth of supermassive black holes. While black holes are commonly found in the centers of galaxies, their growth can be influenced by interactions, mergers, and the inflow of gas. Void galaxies, evolving in isolation, allow scientists to study the natural development of central black holes without external influences. This can reveal whether black holes can grow efficiently in solitary galaxies or whether interactions are essential for their rapid development. The discovery of void galaxies has challenged previous assumptions that galaxies require dense environments to form and evolve. The existence of these isolated galaxies demonstrates that, under the right conditions, galaxies can develop complex structures, form stars, and maintain dynamic systems even when removed from the gravitational influence of massive clusters. This has broadened our understanding of galaxy formation, showing that the universe has multiple pathways for creating the diverse array of galaxies we observe today. Void galaxies also contribute to the study of cosmic expansion and dark energy. As voids grow larger due to the accelerated expansion of the universe, galaxies within them become increasingly isolated. By tracking the distribution and motion of void galaxies over time, astronomers can gain insights into the rate of cosmic expansion and the influence of dark energy on large-scale structure. This makes void galaxies not only interesting from an astrophysical perspective, but also valuable for testing cosmological theories. The properties of void galaxies, including their stellar populations, gas content, chemical composition, and dynamics, continue to be the subject of active research. Advanced telescopes and surveys, including space-based observatories and deep-field imaging programs, have expanded our ability to detect and study these faint, distant objects. The data collected from void galaxies is helping to refine models of galaxy evolution, revealing how isolation and environment shape the life cycles of galaxies over billions of years. Void galaxies can also be used to probe the distribution of intergalactic gas and the large-scale structure of the universe. The gas within voids is often less dense and less enriched with heavy elements than in clustered regions, making it more representative of primordial conditions. By studying how void galaxies interact with this gas, scientists can gain insights into the processes of gas accretion, star formation, and the evolution of galaxies in low-density environments. This adds another layer of understanding to the complex story of cosmic evolution. In summary, void galaxies are extraordinary laboratories for studying the universe in its simplest, most isolated form. They reveal how galaxies can form, evolve, and survive in regions of extreme emptiness, offering a counterpoint to the crowded, chaotic environments of galaxy clusters. Their existence provides crucial evidence for the influence of large-scale gravitational processes, the role of cosmic filaments and tendrils, and the dynamics of cosmic expansion. By observing and analyzing void galaxies, scientists continue to unlock the mysteries of galactic evolution, dark matter, dark energy, and the fundamental structure of the universe, deepening our understanding of the cosmos on every scale. The presence of these galaxies, their delicate connections through filaments and tendrils, their pristine chemical compositions, and their relative isolation make void galaxies a uniquely fascinating subject. Their study combines observational astronomy, theoretical astrophysics, and cosmology, bridging the gap between local galactic phenomena and the grand-scale architecture of the universe. Each discovery of a new void galaxy, each mapping of a tendril or filament within a void, adds another piece to the puzzle of how the universe organizes itself, how galaxies grow and evolve, and how the vast emptiness between cosmic structures plays a vital role in the ongoing story of cosmic history. Galaxies such as MCG Plauser 1 Summer 2C015 exemplify the fascinating remnants of earlier cosmic conditions. Left behind as surrounding matter migrated towards superclusters, they are witnesses to the dynamic evolution of the cosmic web. Studying them reveals how galaxies can persist in relative isolation, forming stars and developing structures with minimal external influence. Observing these galaxies over time can provide insights into long-term evolutionary trends and the effects of cosmic isolation on galactic development, enhancing our understanding of the processes that govern galaxy formation across the universe. The discovery of void filaments has further revolutionized our understanding of cosmic emptiness. These delicate, often straight structures demonstrate that gravity and cosmic dynamics continue to shape matter even in the most underpopulated regions. Filaments and tendrils within voids serve as lifelines, connecting isolated galaxies, channeling gas, and occasionally supporting small clusters. They illustrate the persistence of cosmic structure, showing that even in the vast nothingness, the universe maintains a subtle but meaningful organization. The study of void galaxies, their filaments, and the growth of voids themselves is ongoing, with astronomers continually refining their models of how matter evolves on the larger scales. Advanced simulations, combined with detailed observations, are revealing how voids expand, how isolated galaxies maintain their structures, and how cosmic filaments influence the distribution of matter even in these sparse environments. The interplay between isolation, gravitational dynamics, and cosmic expansion continues to be a key area of research, offering profound insights into the nature of the universe itself. Through these studies, astronomers have begun to appreciate that void galaxies are not merely anomalies or curiosities, but essential components of the cosmic web. They provide critical evidence for understanding how galaxies form and evolve in different environments, how matter is distributed across vast scales, and how the universe's large-scale structure develops over billions of years. Their existence highlights the diversity of galactic environments and the adaptability of cosmic processes, showing that even in extreme isolation, galaxies can thrive and reveal the underlying principles governing the cosmos. Void galaxies also serve as natural laboratories for testing theories of galaxy morphology. Their isolation allows researchers to study the formation of spiral arms, bars, and other structural features without the complicating influence of mergers or tidal interactions. This provides a clearer understanding of the intrinsic mechanisms that shape galaxies and the role of internal dynamics, gas distribution, and dark matter in their evolution. Observations of void galaxies can therefore refine our models of galactic structure and improve our predictions for how galaxies might evolve in various environments. The continuing exploration of void galaxies is expanding our knowledge of the universe in profound ways. By examining the distribution, properties, and evolution of these isolated systems, astronomers can test theories of cosmology, understand the role of dark matter and dark energy, and probe the conditions of the early universe. Void galaxies, with their pristine environments and unique characteristics, offer a window into the simplest and most fundamental processes of galaxy formation, revealing the remarkable adaptability of cosmic structures in the face of extreme isolation. Ultimately, void galaxies embody the resilience of matter and the universality of cosmic forces. Despite existing in regions of extraordinary emptiness, they demonstrate that galaxies can form, evolve, and maintain complex structures even when separated from the dense networks of the cosmic web. Their study continues to illuminate the intricate balance between gravity, dark matter, gas dynamics, and cosmic expansion, providing critical insights into the nature of the universe and the fundamental processes that govern the formation and evolution of galaxies across cosmic time. Galaxies left behind in voids are more than just isolated objects. They are windows into a less disturbed, more pristine universe. Observing their star formation, chemical composition, and dynamics allows scientists to peer into the processes that shaped the earliest galaxies and understand how isolation affects long-term evolution. Their study complements research on galaxies in dense environments, offering a holistic view of galactic development across the full spectrum of cosmic conditions. The connectivity provided by void filaments and tendrils ensures that even the most isolated galaxies are not entirely cut off from the larger universe. These structures allow for the slow transfer of matter and energy, facilitate the formation of small groups of galaxies, and maintain a faint but discernible network within the void. Studying these connections helps astronomers understand how structure and order emerge even in near-empty regions and highlights the subtle but pervasive influence of gravity on cosmic scales. The southern local supervoid is a vast, almost completely empty expanse in the cosmos, stretching across unimaginably immense distances and representing one of the most extreme examples of the voids that pepper the universe. In the grand tapestry of space, it is like a colossal bubble of nothingness, where galaxies are extraordinarily sparse and the usual structures of stars, gas, dust, and galactic clusters are largely absent. While galaxies tend to clump together along filaments and walls, the southern local supervoid stands out as a place where matter is unusually scarce, a giant hollow in the cosmic web that underscores the uneven distribution of matter across the universe. Its emptiness is not merely relative but profound, stretching over a region so vast that conventional imagination struggles to grasp its sheer size, and it contrasts sharply with the bustling regions of space, like the local supercluster, where the Milky Way and hundreds of thousands of other galaxies reside. Positioned adjacent to the local supercluster, the southern local supervoid is like a neighbouring desert next to a thriving, densely populated city in space. The local supercluster itself is a massive collection of galaxies, galaxy clusters, and groups, all gravitationally bound together in an intricate dance across space. It is in this cosmic neighbourhood that our own Milky Way galaxy exists, a galaxy containing hundreds of billions of stars, countless planets, and all the structures and phenomena that have fascinated humans for centuries. Yet just beyond the periphery of this luminous supercluster lies the southern local supervoid, stretching away from these familiar regions into a realm where galaxies are few and far between, and light from stars is far less frequent. This void does not possess the dense clusters, filaments, and walls that are common in the cosmic web. Instead, it forms an almost spherical empty cavity in space, emphasizing how the universe is not uniform but rather a mosaic of extremes, from densely packed regions to vast expanses of near-nothingness. The center of the southern local supervoid is situated at an extraordinary distance from Earth, approximately 96 megaparsecs away. Translating this distance into more familiar terms, a single megaparsec represents about 3,200,000 light-years. Multiplying that out, the center of this void is roughly 308 million light-years away from our planet, an inconceivable span of space that makes the void entirely inaccessible to any human exploration in practical terms. At such a distance, even light, which travels at approximately 300,000 kilometers per second, would take hundreds of millions of years to reach us. This immense separation not only emphasizes the vast scale of cosmic structures, but also highlights how isolated such voids are, lying far from the densely populated regions where galaxies cluster in large numbers. From our perspective, looking across the universe, this void is essentially a massive gap, a nearly transparent region through which only a few galaxies might faintly be observed, dwarfed by the vast distances between them. The dimensions of the southern local supervoid are equally staggering. Across its narrowest width, it stretches about 112 megaparsecs. In more accessible terms, that is around 365 million light-years from one side to the other, even at its smallest cross-section. This measurement itself is almost beyond human comprehension. To put it in perspective, the Milky Way, which is already immense, spans only about 100,000 light-years in diameter. The southern local supervoid, therefore, is more than 3,600 times wider than our galaxy. If we tried to visualize this, the void could easily contain not one, not 10, but thousands of galaxies the size of the Milky Way, and still have enormous empty space remaining. It is as if the Milky Way is a tiny grain of sand lost within a vast, barren desert, stretching endlessly in every direction. The void's actual shape is not perfectly spherical, but even at its narrowest point, its diameter demonstrates the almost incomprehensible emptiness of the region and the extreme rarity of galaxies within it. Estimating the volume of the southern local supervoid yields figures that are astonishing even by cosmic standards. Its volume is roughly 600 billion times the volume of the Milky Way. Considering that the Milky Way itself is already a massive galaxy containing an estimated 100 billion stars, along with gas clouds, dust and dark matter, multiplying that scale by 600 billion creates a number almost impossible to fully comprehend. In terms of sheer spatial capacity, the void is vast enough to accommodate all the stars in the observable universe many times over if they were concentrated within it. Yet the reality is the opposite. This enormous space is almost entirely devoid of matter. It is a place where the gravitational pull of the few galaxies present is insufficient to create the dense clusters and structures seen elsewhere. The emptiness is so profound that it effectively behaves as a counterbalance to the crowded regions of the universe, demonstrating the extraordinary range of matter distribution in the cosmos. The southern local supervoid is part of a larger pattern in the universe, which is composed of filaments, walls, clusters, and voids. While it may seem isolated and unremarkable at first glance, its existence is critical for understanding the cosmic landscape. Void regions like this one help astronomers test the fundamental properties of the universe, including the behavior of dark matter, dark energy, and the expansion rate of the cosmos. Because voids are relatively free from complex gravitational interactions that dominate crowded galaxy clusters, they provide a clearer view of cosmic expansion and the underlying geometry of space-time. Observing how galaxies at the edges of the southern local supervoid move, how their velocities are influenced, and how matter is distributed along its periphery provides invaluable data for understanding the universe's history and its eventual fate. The formation of such a void is tied to the evolution of the universe itself. Following the Big Bang, matter was not evenly distributed but rather slightly irregular, with tiny variations in density. These small fluctuations were amplified over billions of years due to gravity. Regions with slightly more mass attracted even more matter, forming clusters and filaments, while regions with slightly less matter lost density and became the voids we observe today. The southern local supervoid represents one of these areas where the initial density was lower than average, and over cosmic time, it became increasingly empty as surrounding galaxies and matter were pulled into denser areas. In a sense, this void is a fossil record of the early universe, showing us how matter segregated into the intricate cosmic web we now observe. Its enormous scale also implies that the processes governing galaxy formation, matter distribution, and cosmic expansion operate over distances far beyond human intuition, revealing a universe that is both ordered and profoundly vast. Despite its emptiness, the southern local supervoid is not entirely barren. Occasionally, astronomers identify sparse galaxies within its expanse, drifting like isolated islands in a vast cosmic ocean. These galaxies are often smaller, less massive, and less structured than those found in clusters, possibly due to the limited availability of gas and the weak gravitational interactions that would otherwise stimulate star formation. Studying these isolated galaxies provides unique insights into how galaxies evolve when largely unaffected by external influences, contrasting with galaxies in crowded environments where mergers and interactions are frequent. The few galaxies that inhabit the void might have unusual properties, with slower star formation rates, distinct chemical compositions, or irregular shapes, offering natural laboratories for understanding galactic evolution under extreme isolation. From a visual perspective, the southern local supervoid is mostly invisible in conventional telescope images because it lacks the bright, densely packed stars that make galaxies shine in clusters. Its detection relies on mapping the positions of galaxies across vast distances, identifying regions where they are conspicuously absent. Astronomers use redshift surveys, which measure the displacement of light due to the universe's expansion, to determine the distances to galaxies and reveal the large-scale structure of the cosmos. By plotting millions of galaxies in three-dimensional space, the outline of the southern local supervoid emerges as a vast, almost empty bubble, contrasting sharply with the dense filaments and walls surrounding it. The void's scale, shape, and location relative to the local supercluster are determined through painstaking measurements and extensive data collection, often requiring collaboration across multiple observatories and decades of observation. The concept of the southern local supervoid also invites reflection on humanity's place in the cosmos. While the Milky Way, with its hundreds of billions of stars, seems enormous and all-encompassing, it is merely a tiny dot on the periphery of a local supercluster, which in turn is a small part of the universe's vast network of filaments, clusters, and voids. The void itself, stretching hundreds of millions of light-years, dwarfs any structure we are familiar with, highlighting the immense scale of cosmic architecture. Understanding such a void gives perspective not only on the physical size of the universe but also on the processes that shape it, the patterns that emerge from seemingly chaotic distributions of matter, and the subtle interplay between empty and densely populated regions that define the universe's character. The southern local supervoid is also of particular interest for studying dark energy, the mysterious force believed to drive the accelerated expansion of the universe. Because voids are underdense, the gravitational pull from matter is weaker, and the effects of dark energy are more pronounced. Observing how galaxies on the edges of the void move can provide constraints on the properties of dark energy, helping astronomers refine models of cosmic expansion and predict the universe's long-term behavior. Similarly, studying how light travels through the void, including phenomena like gravitational lensing and the integrated Sachs-Wolf effect, allows researchers to test the interaction between light, matter, and the universe's geometry, offering windows into the fundamental laws that govern everything from subatomic particles to galaxies. Comparisons with other cosmic voids also highlight the southern local supervoid's significance. While many voids exist throughout the universe, varying in size, shape, and density, this particular void is one of the closest of its scale to the Milky Way, making it more accessible for detailed study than many distant larger voids. Its proximity allows astronomers to use a wide range of observational tools to map its structure, analyze its sparse galaxy population, and understand how voids interact with their surrounding cosmic environment. By studying it in conjunction with nearby voids, clusters, and superclusters, scientists can build a more complete picture of the cosmic web, understanding how massive structures and vast emptiness coexist, influence one another, and evolve over billions of years. Furthermore, the southern local supervoid illustrates the role of emptiness in shaping the universe. Without such voids, the cosmic web would be dramatically different. Matter would be more uniformly spread, and the intricate filamentary patterns of galaxies might never form. Voids act as counterweights to dense regions, influencing the gravitational landscape and affecting the motion of galaxies even far beyond their boundaries. Their presence impacts the large-scale flow of matter, guiding galaxies into clusters and filaments and shaping the universe's overall structure. In this sense, the void is not simply an empty space but an active player in the dynamics of cosmic evolution, affecting how galaxies cluster, how superclusters form, and how cosmic expansion unfolds across billions of light-years. The southern local supervoid also challenges our perception of emptiness and scale. While the term void suggests nothingness, even a sparse population of galaxies, dark matter, and diffuse gas is enough to reveal complex processes. The void contains a subtle gravitational field, faint traces of intergalactic gas, and the occasional isolated galaxy, all interacting over incomprehensible distances. This subtlety demonstrates that emptiness is not absolute but relative, measured against the dense and vibrant regions of space. Even within this nearly barren region, the laws of physics operate consistently, governing the motion of galaxies, the expansion of space, and the behavior of light, revealing the universe's coherence despite its staggering complexity and scale. The study of the southern local supervoid therefore intertwines observational astronomy, theoretical physics, cosmology, and even philosophy. It represents a natural laboratory for testing theories of galaxy formation, cosmic expansion, and dark energy. It challenges astronomers to measure distances with extraordinary precision, to map the faintest galaxies across hundreds of millions of light-years, and to interpret the sparse data in the context of large-scale structure. Each discovery within or near the void sheds light on how the universe evolved from a nearly uniform state after the Big Bang to the richly structured cosmos we see today. The void's existence reminds us that the universe is a mosaic of extremes: densely packed clusters, intricate filaments, enormous superclusters, and vast expanses of near-nothingness that stretch across incomprehensible distances. Beyond its scientific significance, the southern local supervoid fuels human imagination and curiosity. It is a place where the conventional expectations of crowded galaxies and twinkling stars give way to a vast, silent expanse, evoking awe at the enormity and diversity of the cosmos. It underscores the humbling fact that humanity's home galaxy, the Milky Way, and even our local supercluster occupy only a tiny portion of the universe's grand architecture. Contemplating such a void stretches the mind, forcing a reckoning with scales of space and time that defy ordinary human experience, and highlighting the ingenuity required to study regions so far removed from our immediate surroundings. The void's sheer emptiness and size also provide clues about the universe's past and its possible future. Because voids form from underdense regions, their growth over billions of years is slower than the collapse of matter into clusters. Observing the southern local supervoid's shape, size, and internal dynamics helps astronomers reconstruct the history of matter distribution in this part of the cosmos, providing insight into how the surrounding superclusters pulled matter away and how cosmic expansion has shaped the void. It also helps refine simulations of the universe's evolution, offering a test for models that attempt to replicate the large-scale structure seen today. The behavior of galaxies at the void's edges, the flow of dark matter, and the interaction between sparse gas and radiation all contribute to a fuller understanding of the processes shaping the universe. In addition, the southern local supervoid exemplifies how scale affects our perception of space. On human scales, a region hundreds of millions of light-years across seems impossible to fathom. Yet in the cosmic context, this void is just one of many, with others like the Bhuta's void, the giant void in Cain's Venadisi, and numerous smaller voids scattered throughout the observable universe. Each void differs in size, shape, and density, but collectively they form an essential component of the cosmic web, helping to define the universe's texture and providing contrast to the dense regions of galaxies that dominate our night sky. The southern local supervoid, being relatively close in cosmic terms, serves as a reference point, allowing astronomers to compare voids, understand variations in structure, and study how these vast empty regions influence the universe's evolution. The immense size of the southern local supervoid, also emphasizes the challenges inherent in astronomical observation and measurement. Detecting and studying a structure of such scale requires precise instruments capable of mapping galaxies across hundreds of millions of light-years. It demands careful accounting for redshift effects, calibration of distance measurements, and extensive data analysis to distinguish true emptiness from observational gaps. Astronomers must combine data from multiple surveys, using both optical and radio observations to confirm the void's dimensions, volume, and structure. The successful characterization of the southern local supervoid is a testament to decades of painstaking work, technological advancement, and international collaboration in the field of cosmology. This void also encourages reflection on the distribution of matter and the role of gravity on the larger scales. The contrast between the nearly empty southern local supervoid and the dense local supercluster highlights how matter organizes itself under gravity, forming clusters, filaments, and walls, while leaving vast regions empty. This distribution is not random but follows patterns predicted by models of cosmic inflation, dark matter dynamics, and the growth of structures from initial density fluctuations. Observing how galaxies and matter behave at the boundary of the void allows scientists to test these models and refine our understanding of how the universe came to acquire its present form. The southern local supervoid, with its enormous diameter, extreme emptiness, and proximity to the Milky Way, is a cornerstone in our understanding of cosmic voids. Its study bridges the gap between theoretical predictions and observable phenomena, providing a tangible example of how vast regions of emptiness coexist alongside dense concentrations of galaxies. The void's existence demonstrates the universe's capacity for extremes, where vast nothingness and luminous abundance are intertwined, creating a cosmic landscape of remarkable diversity. Its size, volume, and position make it not only a scientific curiosity, but also a profound symbol of the vastness and complexity of the universe, reminding us of the intricate patterns that govern matter and energy on the largest scales imaginable. In examining the southern local supervoid, astronomers gain insights into the subtle interplay of forces shaping the universe. The underdense nature of the void means that galaxies within and near it experience gravitational influences different from those in clusters or filaments, affecting their velocities, orientations, and interactions. The void serves as a natural laboratory for observing these effects, helping refine models of galaxy dynamics, large-scale structure formation, and cosmic evolution. Its sheer scale and relative isolation make it particularly valuable for testing theoretical predictions about how matter behaves in low-density environments, contributing to a more complete understanding of the universe's composition and the fundamental laws governing it. The southern local supervoid also emphasizes the importance of perspective in cosmology. From within the Milky Way, the universe appears as a sky dotted with countless stars and galaxies. Yet when mapped in 3 dimensions across hundreds of millions of light-years, vast regions like this void become apparent. These empty expanses are as significant as the galaxies themselves in defining the universe's structure. They shape gravitational fields, influence cosmic flows, and provide context for understanding the distribution of dark matter and dark energy. The southern local supervoid, therefore, is not a mere absence of galaxies, but an active component of the cosmic network, exerting subtle but measurable effects on the universe at large. The southern local supervoid is a testament to the scale and diversity of the universe, a region where emptiness dominates and the usual abundance of galaxies is starkly absent. It lies at the boundary of our familiar cosmic neighborhood, next to the local supercluster, yet extends over a distance hundreds of millions of light-years across. Its volume, nearly 600 billion times that of the Milky Way, underscores the immense space encompassed within a void. Its study illuminates fundamental questions about galaxy formation, cosmic expansion, dark energy, and the large-scale structure of the universe, while also providing a humbling perspective on humanity's place in the cosmos. The southern local supervoid, with its vast emptiness and subtle gravitational influence, remains one of the most fascinating and extreme features of our universe, a silent giant stretching across the cosmic landscape. The existence of the southern local supervoid also informs our understanding of the universe's expansion. Because voids are underdense, they expand slightly faster than the average expansion rate of the universe due to the reduced gravitational pull from surrounding matter. This accelerated expansion in underdense regions contributes to the overall dynamics of cosmic evolution, subtly influencing the velocities of nearby galaxies and affecting the large-scale distribution of matter over time. The southern local supervoid, therefore, is not static but slowly changing, its boundaries shifting as the universe continues to expand and evolve. This dynamic behavior illustrates the interplay between empty regions and dense structures, highlighting the ongoing complex processes that shape the cosmos on the grandest scales. The Taurus Void is an enormous, almost entirely empty region of space, a cosmic expanse that stretches for immense distances between two of the largest known structures in the nearby universe, the Perseus-Pisces supercluster on one side and the Virgo supercluster on the other. In the vast cosmic web, where galaxies, clusters and superclusters are interconnected in a delicate, almost spiderweb-like network of filaments and walls, the Taurus Void stands out for its near-total emptiness. It is a place where galaxies are few and far between, where matter seems to thin out to almost nothing, and where the darkness of intergalactic space dominates almost completely. Despite this seeming emptiness, the Taurus Void is remarkable not simply because of its vast scale, but also because of its proximity to our own cosmic neighbourhood, the Milky Way galaxy, and because it plays a crucial role in shaping the structure and boundaries of our own supercluster, the Virgo supercluster, which is the home of our galaxy. In effect, the Taurus Void is not just an empty gap in space, it is a defining feature of the large-scale architecture of the universe in our local region, marking a clear division between colossal structures of matter and influencing the flows and movements of galaxies within and around it. The uniqueness of the Taurus Void is immediately apparent when one considers its location. Compared to the majority of cosmic voids, which tend to be found at enormous distances from Earth, often hundreds of millions or even billions of light-years away, the Taurus Void is relatively close. In astronomical terms, relatively close still implies distances that are almost unimaginable in human terms, but it does mean that this void is within reach of careful observation using our telescopes, both optical and radio, from here on Earth. The Taurus Void's proximity makes it a particularly intriguing target for astronomers who study cosmic structure and evolution, because nearby voids can be observed in more detail, and their influence on surrounding galaxies and superclusters can be studied more directly. In a sense, it is like having a window into the cosmic scaffolding that underlies the observable universe, a region where the contours of emptiness shape the distribution of galaxies around it. Yet, despite this closeness, the Taurus Void has remained somewhat mysterious and difficult to study in detail, a cosmic enigma partly because it lies behind a dense region of our own galaxy. When astronomers try to observe it from Earth, they encounter the so-called zone of avoidance, a swath of sky heavily obscured by the Milky Way's stars, gas and dust, which effectively acts like a thick curtain blocking light from distant objects behind it. The Taurus Void is fascinating not only because of what it lacks, but also because of how sharply it is defined in some directions. In the portion of space where it meets the Perseus-Pisces supercluster, its boundaries are well marked. The galaxy clusters within the Perseus-Pisces supercluster, such as A400, A426, and A374, lie immediately adjacent to the edge of the void, creating a clear demarcation between the region of near-total emptiness and the dense, bustling clusters of galaxies that make up one of the universe's largest coherent structures. By contrast, in the direction where the Taurus Void is obscured by the Milky Way, its boundary is more ambiguous and difficult to determine because much of the light from the galaxies that might inhabit that region is absorbed or scattered before it can reach Earth. This makes it a challenge for astronomers to measure the exact extent and shape of the void, and it has led to some uncertainty in estimates of the void's dimensions and density. Despite these challenges, the void is estimated to be approximately 100 million light-years across, an immense span that dwarfs even the largest clusters of galaxies, stretching across a volume of space so vast that it is almost impossible to imagine in everyday human terms. When seen in the sky from Earth, the Taurus Void occupies a specific region of right ascension and declination, which are coordinates used by astronomers to map the heavens. It appears roughly from 2 hours and 40 minutes to at least 4 hours of right ascension, at which point the view is blocked by the Milky Way, and from 5 degrees to 40 degrees in declination. These coordinates indicate that the void occupies a significant portion of the celestial sphere, but also highlight the difficulty of observing it in its entirety due to the obstruction of our own galaxy. On the side opposite the Milky Way, where the void borders the Perseus-Pisces supercluster, the boundary is sharply defined, making it easier to study the interaction between the void and the surrounding clusters. This contrast between a clearly defined edge and an obscured, ambiguous edge adds an extra layer of complexity to the study of the torus void, as astronomers must combine different types of observations, including optical, infrared, and radio, to piece together a complete picture of this enormous empty space. In three-dimensional terms, the torus void occupies a position between the Perseus-Pisces supercluster and the Virgo supercluster, situating itself as a cosmic gap in the web of the local universe. This position is particularly important because the void, along with its neighbouring structure, the local void, helps define the boundary between these superclusters. The Virgo supercluster, which contains our own Milky Way galaxy, is itself part of an even larger structure called the Laniakea supercluster, a massive network of galaxies and clusters stretching across hundreds of millions of light-years. By forming a low-density region between these colossal structures, the torus void influences the flow of galaxies and dark matter, guiding their motion along the edges of the void and contributing to the overall dynamics of the local universe. In a sense, the torus void functions like a cosmic moat, creating space in which matter is relatively sparse, while simultaneously shaping the distribution of galaxies in the surrounding superclusters. One of the primary difficulties in studying the torus void stems from its position behind the zone of avoidance, which lies in the plane of the Milky Way. The zone of avoidance is an area where interstellar dust and gas in our galaxy block light from more distant galaxies, making them difficult or impossible to detect in visible wavelengths. For the torus void, this means that astronomers cannot simply look through telescopes at optical wavelengths and expect to see all of the galaxies that might lie within or beyond the void. Dimmer galaxies, which would normally contribute to a map of the void's density, may be obscured completely, leading to the possibility that the void appears emptier than it truly is. This issue, known as extinction, is a fundamental challenge for studying any cosmic void located near or behind the plane of the Milky Way. However, the apparent emptiness of the torus void does not mean that it is not a real void. Scientists have employed alternative observational methods to confirm its existence. One approach is to observe the void in the infrared spectrum, which is less affected by the dust and gas of the Milky Way. Infrared observations can penetrate the foreground obscuration to reveal galaxies that might otherwise remain hidden, allowing astronomers to verify that the torus void is indeed a region of low galaxy density. Over the years, multiple studies have used infrared and radio data to map the torus void, tracking not only the presence or absence of galaxies, but also the flows of galaxies moving outward from the void into adjacent superclusters. These observations provide strong evidence that the void is a genuine structure in the universe, a vast pocket of space where matter is unusually sparse, rather than a simple artifact of observational limitations. Mapping the torus void has also involved measuring the rate at which galaxies move away from the void, a phenomenon influenced by gravitational forces. Because voids are underdense regions, they exert less gravitational pull than surrounding areas with more matter. As a result, galaxies near the edges of the torus void tend to move outward toward regions of higher density, such as the Perseus-Pisces supercluster or the Virgo supercluster. By analysing these motions, astronomers can infer the shape and extent of the void, even when some regions remain hidden behind the Milky Way. The combination of direct observations in multiple wavelengths and indirect measurements based on galaxy motion has allowed scientists to construct increasingly accurate models of the torus void, despite the persistent challenges posed by the zone of avoidance. Future efforts to study the torus void promise to improve our understanding even further. Two major surveys, known as AlphaZoa and Alfalfa, have been designed to look at regions of the sky that are difficult to observe with optical telescopes. Both surveys use the Arecibo radio telescope to detect hydrogen emissions from distant galaxies, focusing on light that has been redshifted due to the expansion of the universe. This technique allows astronomers to detect galaxies that are otherwise invisible because their light has been absorbed or scattered by interstellar dust in the Milky Way. By observing in radio wavelengths, the AlphaZoa and Alfalfa surveys can penetrate the zone of avoidance and map galaxies behind it with much greater precision. These surveys are limited by the operational constraints of the Arecibo telescope, which restricts the range of declination that can be observed. But within these limits, they offer the potential to refine measurements of the torus void's dimensions and density. The scientific significance of the torus void extends beyond simply cataloguing an empty region of space. As one of the nearest large voids to the Milky Way, it provides a natural laboratory for studying the behavior of matter in low-density environments, the dynamics of galaxy motion near voids, and the large-scale structure of the universe. By understanding voids like Taurus, astronomers can gain insights into the formation and evolution of galaxies, the distribution of dark matter, and the influence of cosmic voids on the expansion of the universe. Moreover, because the torus void helps define the boundary between the Virgo supercluster and the Perseus-Pisces supercluster, it also contributes to our understanding of how superclusters themselves are organized and connected. In this way, studying the torus void is not merely an exercise in mapping emptiness, it is an exploration of the fundamental architecture of the cosmos, revealing how vast regions of space devoid of galaxies can exert a subtle but important influence on the universe at large. The observational challenges presented by the torus void highlight an important aspect of modern astronomy. The universe is not always easy to see. Even when a cosmic feature is relatively close by in astronomical terms, it can remain hidden from view behind the intervening matter of our own galaxy. Overcoming these obstacles requires the use of multiple wavelengths of light, sophisticated survey techniques, and careful analysis of galaxy motions and distributions. Infrared and radio observations in particular have proven essential for studying regions like the torus void, where visible light is blocked. By combining these methods, astronomers are able to construct a three-dimensional map of the void and better understand its true size, shape, and density, despite the obstructions that complicate direct observation.